Good morning, good afternoon, and good evening, everybody. Welcome to the Optimism Future of Ethereum Summits. We're really excited to be going live here with so many awesome talks about the Optimism ecosystem. Optimism is a huge partner of ETH Global's over the last couple of years, and we're really excited to be working so closely with them to celebrate an important part of the Optimism journey, as well as chat about the newest things that are coming down the pipeline for the scaling solution known as Optimism. So thank you everybody for being here. My name is Jacob. I'm part of the ETH Global team. I'm also an Optimism delegate. And I'm also going to be joined today as MC by Katie, who'll be joining in just a second. Thank you everybody for coming online on our ETHglobal.tv platform. This is a really nice way to interact with everybody. Feel free to log in and join the conversation, ask any questions as people are going through their talks, and we will relay those to the different speakers. And of course, feel free to enjoy some lo-fi beats during any of the breaks throughout the week or throughout the session. So as I mentioned, Katie's joining me as one of the MCs today. Katie works for the UDHC team and also is an Optimism delegate. So we're really excited to have representation on the Optimism DAO side here as well. And together we'll be popping in today to go through the different sessions. So just wanted to give a quick little overview of today's schedule. So we have Carl joining us in just a minute to talk about the modular Optimism stack, OP stack. We have Joshua to do an introduction to architecture of Optimism, as well as chat a little bit about Bedrock, the next upgrade. We have NorSwap joining us at 1:00 p.m. Eastern to talk about modular sequencing, followed by Proto Lambda joining us for pluggable data availability at 1:30. After that, we have a really cool panel at 2 p.m. Eastern on the state of EIP 4844, joined by Tim Biko, Terence Shao, Mofi, and Roberto Bayardo of the Coinbase team. And finally, a cool overview of one of the major products that is completely built on Optimism, which is Quix, their NFT marketplace. So Mark Dawson, founder of Quix, is going to come and chat at 2:45 about what they're working on there. So without further ado, would love to welcome Carl onto the stage. So Carl, whenever you're ready, feel free to unmute and share your screen. Carl is listed on this chat as Carl with many OP with many exclamation points. So you know he's excited. There you go. Welcome to the chat, Carl.
You already know. How could I not be? Oh my goodness. Let me make sure that okay. I got all the things.
You're all set?
I'm all set. We did awesome. It, Reddit.
There you go. Everything looks great.
Right.
Well, I'll get out of the way and excited to hear more about the OP stack.
Okie dokie. So welcome everybody. Going to talk about the OP stack, Bedrock, and the rise of the super chain. And we actually got a solid amount of time. I didn't realize we had so much time, but I got to fill up all the time. So without further ado, I'm Carl. Of course, I work at OP Labs doing this Optimism stuff. And so now, whenever I give this or whenever I talk about these things, right, these words pop up on the screen, there's one word that everyone sees. They don't see the rest of the words. They see superchain. That is what they see realistically. So I'm not going to start off by talking about the superchain. I'm not going to talk about how it is, all these chains kind of combined into one super duper fantastic thing. I'm not going to talk about that to begin with. Instead, what I'm going to talk about is the problem. Ethereum congestion back in 2016, 2015. This has been a problem for way too long. Oh my God. It's been a long many years. But we've had too much demand for Ethereum. Ethereum is too good. And so what happened? How did we solve Ethereum congestion, realistically speaking? Well, we copy and pasted it into more chains, all these various chains generated by Dolly 2. That is what we did. And then what did we do? Well, we connected these chains with largely insecure bridges, these largely insecure chains, realistically speaking, and we kind of hacked some together to address this horrible problem of congestion. And in some sense, Optimism is kind of one of these things, right? It is a layer 2, but from a user experience perspective, it still has a bridge. It still, feels a little bit distinct. But it does have the nice quality of being rooted in Ethereum and in sharing some of that security. And so, right, this is kind of the state of affairs in some sense. And, if I'm a user, this like cute little gerbil also generated most of these photos are generated actually. Then you're, going from one chain to another, trying to like deposit, withdraw. It's just kind of chaos, to be honest with you. And you can kind of visualize this as a crazy like market, right? It's like a marketplace, and you're going from these different sellers, and maybe you go to this person, you're transacting on this chain using this vendor, and behind you there's a bridge that just exploded and another one that just exploded, and then you went to this other chain, and now it's actually a rug pull. Like, it is true and utter chaos right now. This is not good. This is not a user experience worth bragging about, right? This is just honestly very sad. But it's better than no one being able to transact, which is the alternative, because Ethereum was just way too congested. But we can do better. We can do better. And what if I told you that there was a solution to this problem? There was a solution where instead of going from one place to another, everything is all in one place. And you don't have to transact with all these different, vendors. You can instead transact with one trusted seller. And you've got seamless atomic checkout in this market. Well, it's the supermarket. Dun, 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 dun. Whoa. Oh my gosh. Okay, this is a joke, right? We're not here for supermarket technology. But it's just, supermarket, super chain. Anyway, really though, I can't help myself. Our chain should have these properties, right? We demand these properties that, everything in one place, a single trusted seller, so you're not getting hacked all the time, right? We shouldn't have to bridge from one chain to another. We shouldn't have to get hacked. I mean, my goodness, that's a low bar. And also transaction fees should be cheap and sometimes pretty much free. Like, that is legitimately, there is no technical blocker. And so there is no reason why we should not achieve this. Don't fear, though. Don't fear. The OP stack is here. All right. We finally got to the actual meat of the talk to an extent. Well, state of affairs, kind of crazy. Absolute madness. But we can fix this. How do we fix this? Well, we can build standardized open source libraries that provide shared security, so things are actually secured, rooted in Ethereum. There are fallback mechanisms. There are things that prevent terrible hacks. Also, just the fact that it's standardized makes it way more secure, because now there are way more eyes on it. It's not just a one-off solution, because that's how you get hacks. Additionally, composable, right? We need these systems to all work together. You can swap out one module. They're compatible with one another. And additionally, finally, coordinated sequencing. I won't talk about how incredibly that important that is, but it is actually incredibly important for creating an experience. Now, what is this experience that the user, at the end of the day, right? All of this technology is in service of building something that we can all use, right? I want to use a better product than we have today. And so what is the user experience of this system? Well, you actually, with the compatibility that this, the shared technology enables, we can actually create a virtualized single superchain, right? We can actually interact with the system in a way where you're not having a bunch of user-facing bridging. All that kind of stuff can be handled in the background, right? We can have robust modules that ensure security, and additionally, it should be hella scalable, with horizontally scalable. Some call it, quote, infinitely scalable, but I feel like that's just like a savage marketing term. Horizontally scalable, so we can have near free transactions that essentially cost the amount of money that it costs to run that transaction on a computer. So it's like renting from AWS as opposed to paying surge pricing on Uber. So we can realize this super chain. We can realize it with open source technology, shared standards, and working together. And we can make that happy experience for our happy gerbil. Now, if we want to talk about how exactly the kind of like combination, the virtualization of the superchain works, you can kind of take a look at Endgame that has a bit of a hint at it. And then there's even more talks that we can go into, but I won't do it right now because we don't have enough time, or at least so I thought. But you can ask questions at the end of the presentation. So now we are past the intro. Maybe I needed all the time that we have. Let's talk about the core of the OP stack. So this is not necessarily everything, but this is the kind of bread and butter. Okay, what is the OP stack? Again, standardized open source modules for layer 2 chains. We are using it for, of course, Optimism mainnet, but it is open source, therefore anyone can mess around. Now, there are 3 key layers to this, right? Any stack has some layers: the consensus layer, the execution layer, and the settlement layer. Consensus, that's how the chain gets the chain gets constructed. The execution, that's the virtual machine that is actually being, executed over this chain of inputs. And finally, the settlement layer, that's how withdrawals occur. So if you look into layer 1, if you look closely with a magnifying glass, you will see that layer 1 is actually made up of its own consensus layer and execution layer. So this is a recent change that we've modularized layer 1 in the very same way that we're trying to modularize the layer 2 technology. And the way that that works is that we have Prism, these consensus layer clients, not just Prism. Don't just use Prism, y'all. We need diversity. Additionally, we have execution layer clients like Geth. And we have that same structure playing out in layer 2 as well. Now, let's get into the nitty-gritty of the consensus layer, execution layer, and settlement layer. What are these different things? So first, for the consensus layer, we have 2 key modules, 2 options that we can choose from. We can either choose rollup, which basically means that all the transaction data is fully available on chain, or Plasma. Now, Plasma got a bad rap back in the day. It was just too early. And now there's a million different terms for Plasma, like Validium, all of these things, the various things. Basically, at the end of the day, we should just call them data availability challenges. We have a consensus layer client that has off-chain data with data availability challenges on chain. So those are our 2 kind of like broad categories of consensus layer type deals. Additionally, we've got execution layer. So that is the EVM, the classic one, right? We've also got extra fancy ones like this weird one in the middle that I'm kind of just like hinting at, but not saying because I don't know if I should talk about it yet. But anyway, we've got other execution clients that are special purpose, maybe for some games, maybe not, whatever. And then finally, we have the settlement layer. This is how things actually get withdrawn from the system. This is how you kind of prove the withdrawal. Now, notably, I have here multisig, fault, and ZK proof. I am writing this as though the settlement layer is, if you have a fault proof or a ZK proof that is, kind of working, but you still have a fallback to a multi-sig, then because of lowest, the weakest link security, at the end of the day, you're still multi-sig. And so that's why multi-sig is here. Obviously, no one wants multi-sig to persist into the future, but the reality of layer 2 right now is that things are being secured, withdrawals are being secured by the multi-sigs, which is, it's better than it being secured by an insecure proof system. So let's be thankful. Anyway, consensus layer, execution layer, and settlement layer, right? You can choose each one of these. And, if you choose this configuration, then you'll end up with an EVM equivalent optimistic rollup, right? This is the perfect flagship for an L2, but it's not necessarily the only configuration you might ever want. And it does have different security trade-offs. Or withdrawal trade-offs, right? All of these things are trade-offs. Now, additionally, right, eventually you'd want to plug in potentially a ZK rollup, a ZK proof system, a ZK settlement layer. And so what that means is that we can have an EVM equivalent ZK rollup. And additionally, because it is modular, we can swap it in and swap it out. So the same chain that was running a fault proof can without changing anything about a developer experience, without changing anything about, the nodes that people are running, you can actually swap in a different proof system for withdrawals. And so that means that we can get these like seamless upgrades and write compatible software. Actually, in fact, the key to scaling up the production of software is defining really good abstraction layers. And so, this is actually more important than you might imagine, because it allows people to work on different things in silos and still be compatible once they have done the incredible amount of work. And ZKPs are a great example of something that's going to take a lot of work to make extremely inexpensive. And let's continue. So we've got the consensus layer, right? We can do things like layer 3 by layering in Plasma with the EVM and fault proofs, right? All of these things are options, and even swap out the execution layer. All of these, configurations are valid. But the key is that we should make sure that the way that they communicate, the way that these layers communicate with one another, is standardized so that we can all benefit from each other's innovations and build out the blockchain stack, candidly, in an open source and permissionless way. So that is the core of the OPISL stack ISL. So the Bedrock release. We are finally at that section. Okay, what is Bedrock, right? Bedrock is a major step forward across two primary dimensions. So first off, obviously, it is the next upgrade to Optimism mainnet. That is, we are upgrading our mainnet. If you deposit into Optimism, then that thing is going to be using Bedrock very, very soon. And that's going to make it the most, literally like the most secure, the most scalable rollup that is out there. Let's go. So Bedrock is actually legitimately extremely, extremely dope. The second thing is that it is a foundational, it supplies the foundational OP stack modules, right? We built it out in this modular way already. And in fact, in the later talks, with Josh, with et cetera, we'll go into the details of like how these things actually fit together and what components we built. So, right, we have a configuration of the OP stack, and we have all of these different packages which it is using, right? We have this OP node, which is the consensus layer kind of equivalent. We have OP Geth. We even have OP Aragon, right? This is literally 2 Ethereum clients that are compatible. Additionally, we've got all of these other, Batcher Proposer contracts. We have Canon for fault proofs. All of these things are built in this modular way. And so here, I'll go over into like more specific details of like where the major steps forward in modularity are. So first off, modular execution with the engine API. So first, I started this talk by saying how the consensus layer and the execution layer are actually being, built out and were created for layer 1 development. Well, what did we do? Well, we swapped out the consensus layer and replaced it with the OP node. So now we're coming to consensus by using L1 consensus. That's literally like the definition of layer 2. Additionally, we have the execution layer. So we have Geth. But we can also swap in things like Aragon, and it takes very little code to modify these execution layer clients to support layer 2s. And that is critical, right? Code reuse is a key factor of security, and these systems need to be more secure than any other system you've used. Let me tell you, it is. These security requirements are insane. And so this also enables us to have a multi-client ecosystem. We would never have made the merge upgrade. We would never have done the merge upgrade without multiple clients, because multiple clients catch divergences between them, making the entire system more secure. That's why the merge went through without any critical bug reports, right? That is literally the technology, that the security technology they used was a multi-client ecosystem. And so we need that very same thing for layer 2. And that is absolutely critical if we want to enable fault proofs, for instance. And I'll talk about that a little bit more later. So yes, additionally, we can even have more fun, and maybe it's not going to have a multi-client ecosystem, but we can input this like weird mystery VM, and boom, now we've got even more execution engines that we can use. So that is the first step, right? It's the engine API. The second thing is modular derivation. So first, execution. The second one is derivation, or the consensus layer. So in back in the good old days, a year and something ago, when we were writing our rollups, we thought that we needed a bunch of smart contracts on layer one to actually derive the rollup. So essentially, you take in L1, this function, right, is like the rollup function. It produces the layer 2 blocks, and what we were doing is we were saying, okay, you need layer 1, and you need some smart contracts on layer 1 to do some like management for you, and whatever. But this meant that the system was actually really brittle. It was really hard to upgrade because you always needed to maintain these layer 1 contracts. But now what we're doing is we're consuming raw layer 1 blocks, raw layer 1 block data to produce the layer 2 chain. So what does that actually mean? It means that we can swap in, because it's just like a raw stream of data, we can swap in new data sources like EIP 4844 or even Plasma, right? Things like off-chain sources of data. So this allows us to, both scale up, be ready for when we're improving layer 1, because we're pushing forward EIP 4844, which is a major improvement to layer 1. But we're also able to support things like layer 3. And finally, modular proofs with Cannon, right? Cannon it generates the execution trace over the client, and it allows us to prove that execution trace, but we can prove an execution trace with either fault proofs or ZK proofs, right? These two things totally work. The ZK proofs might be too expensive right now, but that's something that we can work on over time. And importantly, Bedrock again supports multiple clients, and multiple clients is incredibly important to support production high security chains, and specifically to support fault proofs and ZK proofs without big bad upgrade keys, right? We need our upgrade keys to be, upgrade, and then you wait like 2 months because you can actually withdraw. And we need them to make sure that the mechanism that allows people to withdraw from layer 2 in case there's a malicious upgrade, we need to make sure that that mechanism will never break. And the only way to make sure that mechanism will never break is with multi-client support. So there we go. More information on that in our pragmatic path to decentralization, because we need to get rid of those upgrade keys. We need to not be multi-sig rollups. Anyway, great. This evolution, right? The state of affairs, this madness with these bridges going crazy and these different chains and this terrible user experience. We're already making progress there, right? Bedrock release is fast approaching. We're about to take a massive step forward in the OP stack. Additionally, we already have multiple OP-based chains. So it's like this is not even like we need more OP chains. Like literally we accidentally had people deploy OP chains just because we were writing our software out in the open. And additionally, we've got teams experimenting with Bedrock, pushing the boundaries of what was possible on chain, right? We're going to break through even the scalability that we have today is not even close to what we're going to have tomorrow. It's like you don't think about the resource constraints on AWS unless you're a massive, crazy, team, but you don't really think about the scalability constraints on AWS as an average individual. You should not be thinking about the scalability constraints as, you're transacting or deploying dApps to a blockchain. This is just the beginning, right? We are about to take over with the zombie horde of gerbils generated by artificial intelligence. We will take over the game. And soon we will realize the final evolution of blockchain. Walmart, no, I'm just kidding. We will finally realize the super chain. Thanks to the OP stack, because we're working together to solve the problems in a secure and scalable way. Hallelujah. We're going to provide that good user experience to us because we're the users too, And The rise of the superchain. That's it. And by the way, this is also a superchain image, but including a gerbil. And I just love the way that these AIs, or like Dolly specifically, cannot spell. It's so good. Anyway, thanks everybody. I guess we don't have that much time for questions, but happy to answer them. Oh, Pizzle, stack Izzle. Let's go. All right, that's it. I mean, I don't know. I'm now in my room. I still feel like I'm in my room. Is there a place I should be looking for like questions? Do we have like a couple, like, you know, I don't know. I don't even know. I don't know where I am. Well, I feel so alone. Wait, am I? Oh, it's because I turned off my mic because I can't hear, maybe? Hello. Okay, fine. I'll just talk then.
Hey, Carl. Sorry.
Oh, great.
No, I think. Hi, it's me. No, I think I don't see any questions. I think we're good. Let me check.
All right,
again.
Sounds good. Well, thanks.
I guess we can open it up really quick. Does anyone have any questions they want to ask Carl?
How did you find such a cute dog photo? Well,
Yeah,
type
that
in
would be my question.
dog on Google. All right, let's move to Josh.
Yes. Okay, awesome. Carl, thank you so much. I love your presentations. You're so enthusiastic.
Thank you.
You're awesome. Okay, cool. Hi, everyone. I'm Katie. So up next, we have Joshua Gutau, who is going to be giving us an introduction to architecture. Oh, hold on. Here we go. Here we go. Okay, so we have Joshua Gutau giving us Introduction to Architecture. Josh, welcome. Thank you so much for being here. I'll let you take it away.
Awesome. Well, let's see, can I get my slides up? Okay, slides up. Cool. Awesome. Hello, everyone. My name is Joshua, and I'm going to be talking about Introduction to Architecture. This is actually a little less architecture in terms of buildings and cool shapes in the sky, but this is going to be about software architecture. And then more specifically, Bedrock's architecture. And as Carl is talking about the various components of the OP stack, this is going to really highlight how Bedrock, the system, fits together and all of the different pieces there. Cool. So the introduction. So today I'm going to be talking about what even is Optimism Bedrock. Carl's talked on that, but I'll expand on that a little bit more. I'm going to give an overview of the system, both of kind of like the components and also the actors. So we have a bunch of different pieces, but some of them do different things. Then we'll go through the rollup node, which is one of the components, the sequencer and the batcher. Then the proposer fault-proof challenge agent. So that's all of the stuff that enables withdrawals. We'll go through a couple data flows and then go through some kind of final implementation notes at the end. So what even is Optimism Bedrock? Bedrock is a network upgrade to reduce fees and increase implementation simplicity. So I'll kind of go through a little bit word by word because it's a big complex sentence with a lot underneath of it. So network upgrade. So Bedrock is going to be kind of a point-in-time release. The thing we'll have, like, we have our current system, we'll have the Bedrock release, and then we'll have more releases in the future. So the network is still Optimism, and this is just the network upgrade. And as part of a network upgrade, we'll be keeping all of the history with Optimism Network. This is just one more step in improving the user experience. And specifically, the biggest change to the user experience is going to be reduced fees. And then the non-changes to the user experience are going to be increased implementation simplicity. This is something that most users won't see, but really improves the performance, improves the reliability, enables a lot of other things down the line. So how do we get there? Bedrock achieves this by redesigning the rollup architecture. So a lot of the things from the previous system kind of are getting modified, and then we're drawing a lot of like new lines between different components inside the system and really making sure that everything fits together in a way we're happy with, and also in a way that kind of enables different components to be swapped in, swapped out, how components can be tested by themselves, and making sure that everything fits together very neatly. So now we get into the fun part, which is the architecture. So we're going to go through the system overview. So here's kind of the discrete components. You have a rollup node. This is OP node, and then there's the execution engine, OP-Geth. We put OP in front of everything because why not? The batcher is the OP batcher. The proposer is OP proposer, and then we don't have a challenge agent, and the fault proof is canon. So OP node and OP-Geth are kind of the things that produce blocks in. That's like your full node on Ethereum. OP batcher submits L2 transactions to L1. Then the proposer submits output routes. And this is what enables withdrawals. And then we talked a little bit about canon, and have talked more about canon in the past, but that is the fault proof system. And the challenge agent is just a simple agent that interacts with the fault proof system. Cool. So those are different code bases and components. How do they translate to the actors? So the actor is someone running, so you can run a multiple code base lots of times. So verifiers, that's a full node. So there's going to be a lot of those. That's just like running your full node on Ethereum. And to do that, you need your OP node, which is like your consensus client, as well as your OP-Geth, which is your execution client. Then you have the sequencer, which is a full node that is mining. And so it produces blocks, and then it also gossips them out and does a couple small things, but under the hood, it's very similar to the verifiers. And then you have your batcher, which is an actor that just maps straight back to the code base. Same with your proposer, and then your challenge agents as well. The sequencer and verifiers actually have to map to a couple code bases because they're more complex things. So, giant diagram time. So this is going through how all of these actors interact. So if you want to kind of deposit into the system, we'll just follow that execution flow. So the user sends a deposit transaction to layer 1, and then the sequencer reads the deposit. Sequencer also then gets transactions kind of separately. Then it creates the new blocks, sequences them. The batcher then picks, and that's kind of how you get deposits. Now, once you have your L2 transactions included, a user sends them to the verifier, they get to the sequencer, you create your blocks, the batcher submits the batches. Now then the verifier reads both the deposit and the batches, and then it derives a chain that matches the sequencer. And so that's kind of the transaction flow. There's a lot of moving parts here, but that's kind of what it is. And we'll go through some of these flows in a little more depth later on. And then when you're doing output proposals, the output proposer reads the state root from the verifier and then just submits it to L1. And that's the OP proposer. And then the challenge agent would interact, would kind of use the verifier, again, looking at the state root and comparing it against what got submitted on L1. And so it's reading between the verifier and L1. And those are, again, all the system actors and how they interact. Cool. So time to dig deep into the rollup node. So it does several things. Reads data from L1, has both deposits and batches. As Carl mentioned, it uses the L2, the engine API to talk to kind of the execution client, OPGEF. There's a P2P network. I'll talk a bit more about that later. And then just as an implementation, it's way simpler than the current L2 Geth implementation. It's a lot closer to upstream, and it's a lot easier to work with. So the diagram. So this is basically all of the components that you need to run a replica or a sequencer. Just a node on Optimism, a full node on the Optimism network. So on the Ethereum side, you have your consensus client and your execution client. They talk to each other using the engine API. And then your OP node, which mirrors the consensus client, uses just your standard ETH JSON RPC. So it does stuff like gets blocks, gets transactions, gets transaction receipts, just kind of essentially reading in the chain data from L1. And then it talks to the L2 execution API, L2 execution engine through a very slightly modified engine API. It's very similar, but I'll talk through a couple of modifications there. And then the OP-Geth or L2 Geth is a small diff on top of Geth. It's actually a little larger than 500 lines right now, but not really that much more. And so that's a lot easier to work with and keep the OP-Geth up to date with upstream, so we can bring in a lot of those improvements a lot faster than if we had done a lot more modifications to that. And so this is a single node. So now what happens when you have multiple of these nodes? So this is where every node is talking to almost every other node. So the vertical lines there basically maps back to the previous diagram, and horizontal lines map back to the previous diagram. And so the top line and the bottom line are two different sets of nodes. So on the left here, you have different consensus clients for Ethereum talking to each other through the beacon chain. Then L1 clients on Ethereum have a sync protocol. They have a transaction pool. And then on the L2 side, we gossip out L2 blocks for the OP node. And then we actually use a lot of the same sync mechanisms, transaction pools, all of that when L2 execution engines are talking to each other. So getting into the details of this engine API, which is what connects the OP node to OP-Geth. It has two extensions, and these extensions are to some of the payload attributes or like fields. So we have two more fields when we're calling fork choice update, but the rest of it's basically the same. And the engine API is actually really simple. There's 4 calls, one of which we don't use at all because we don't have a transition, so it's just not relevant. To the new payload call is just insert a new block into the execution layer. Simple. Fork choice update is a little more complex because it does 2 things at once. It sets a head block, including kind of safe and finalized blocks. And it also, if you give it an optional parameter, it starts the block building process and it returns back kind of reference to that in-flight block. And if you want to get that in-flight block that it's building, you just call get payload. And that's basically it. This is pretty standard API. It's specified by Ethereum, and it makes it really easy to include new execution clients. OP Aragon, that's not that much work to port over 1,000-line diff. And then eventually, we only have one rollup node right now, but it wouldn't be that hard to create a new rollup node that spoke this API and worked with any execution engine. So deposits and batches. So we've briefly spoken about deposits as kind of a way to get money into L2. These are going to be a lot faster now because we're reading them a lot closer to the chain tip. But they also serve another purpose. And the sequencer basically cannot delay deposits outside of a certain range and has to eventually include them. If you're interested in more details about the specifics of how this works. I gave a talk at ETHCC that does a really deep dive into Bedrock and goes through all of this and why this is true. But the net result of this is that the chain advances even if the sequencer doesn't want it to. And then this enables censorship resistance. And then if you never had a sequencer again, you could still unwind the chain through deposits. So deposits also do a lot more than just mint money on L2. They're fully featured transactions. So anything you can do with a normal transaction, you can do with a deposit. And so typically, you actually wouldn't use deposits that much to do this because deposits just get included on L1 kind of one transaction at a time and actually have some state execution on L1 versus a kind of direct L2 transaction. When we batch those, we take a bunch of those, we compress them, and then we just shove it in call data of L1. So direct L2 transactions tend to be cheaper, and that's kind of the typical flow. But if you need to, deposits are always there. Okay, P2P. So here we kind of described how sequencers gossips out blocks. And so the feature that's enabled here is that if you're just a replica on the network and you're subscribing to these unsafe blocks or blocks that have the sequencer has just created, your view of the network is incredibly up to date. And so you can choose to insert these blocks. Now, as part of kind of inserting these blocks, we don't actually mark these as fully safe because there's no guarantee that the block that you received will kind of get submitted to L1. So we prefer in the rollup node, whatever gets submitted to L1 over what the sequencer says. And kind of as a result of this, it's a very minimal trust assumption to insert these blocks and stay up to sync with the tip of the chain. They have a really good user experience without actually sacrificing trust. And this is kind of a similar thing to the liveness in Ethereum, where you have a head block, which could reorg, but then you have your safe block, which is assumed not to reorg, and then you have your finalized block, which will never reorg. And so we've brought over the same kind of terminology and same usage of the engine API to mark blocks as safe, which are very likely to not reorg, finalized, which will never reorg, and then your head block, which you've got from the sequencer, which is likely to be included, but it could change. And that's kind of the whole P2P subsystem. And then as a part of a result of getting these blocks as they're distributed, it's really easy to hook into a snap sync. It's not yet implemented because you can just re-execute all the blocks, but that's something where this architecture of splitting out the execution engine from the consensus layer, that's something that's really easy to do and something we will be doing in the future. Cool. So we've covered the rollup node, talked about OP-Geth and the OP node, how they interact and how different nodes interact with each other on the network. And now we're going to talk about the sequencer and the batcher. So what's here is basically talking about the sequencer, which a normal node essentially. It runs a mining process. And then it's like, just like Ethereum, how every full node has mining code in it. There's all, like every rollup node will also have mining code in it. And there's just one specific one that can run. And then the batcher is a pretty simple code base, just takes L2 blocks, transforms them to the data that you expect, does compression, that's how you get low fees, and then just submits them onto L1. Easy peasy. And then having that be so easy is basically like small modular architecture. That's a theme here. So now the proposer, fault proofs, and challenge agents. So this is a group of kind of three, which will be at least 3 different code bases and a couple different agents. But what's here is this is everything that's required to enable withdrawals. So the proposer is kind of the entry point into withdrawals. So it reads state from L2 and then puts it onto L1. And then after if you put it onto L1 and no one says this is invalid, it's then assumed to be valid. That's the optimistic part of our rollup. And that kind of validity then enables withdrawals. And if it's not valid, then you go through the challenge game and the fault proof. So it's not yet live. See some Canon talks that NorSwap's given for more information about this. But the fault proof is what secures the bridge. This is how you say someone submits something that's invalid as a proposer. The fault proof is what marks it as invalid. And we time bound how long you have to say, hey, this is invalid, so you can actually eventually withdraw. But it still needs some amount of time for the finalization period to basically have enough time that no one can censor the chain for long enough with this withdrawal period. So if it's like a 10-second finalization period, you could censor the chain and then get any fake output through. With a week, you can't censor the chain for a week. And then if there's ever an invalid output proposal, it will be caught. And then, so the actual fault proof game is super fun and exciting, and I'll nerd out a little bit over it. So the entire thing is called Canon, and it has its whole own sub-architecture, and it's like a lot of interesting things in there. But it's an interactive proof game over a MIPS execution trace. So like everything here, it's a lot summarized into a short sentence. So the interactive proof game is kind of this binary search-like thing. So you start out with some code, you execute the code, and you can imagine the code is like executing an instruction, like an add, a subtraction, a load from memory. And so what we do is we have kind of an on-chain version of this, and then your two off-chain components. The two off-chain people both run their execution, your challenger and your defender. So the defender is the person that submitted the output proposal, and your challenger is the person that says, no, this is invalid. And at each, you run the execution trace, and you agree on the start and disagree on the end. And then you can kind of Merkleize the state, do some funky things in there, and then basically run a binary search over like, okay, we agree at this step, we disagree at this step, and then you can finally narrow it down to a single instruction execution, and then execute that single instruction on chain. It's super fun, super interesting, and then actually enables you to kind of fault-proof really complex things really easily. So anything that's deterministic and compiles to MIPS can be fault-proven. So the whole derivation process is going to get imported to Canon. All of the EVM is going to get imported to Canon, and we'll kind of go through the fault proof. Any compression we do, again, just straight through. So we don't have to deal with like loading up data. We can load in the raw data that the rollup node uses, which is again just transactions and blocks. And so those are really easy to kind of load up on chain and prove that, hey, this is actually the block hash on chain. And so that's basically all of that. Super fun, super interesting. Not yet live, but we're working a bunch on that. Okay. Getting back here. Okay, so that's how we secure the system. So I'm going to go through some data flows in the system. You'll see how kind of different things interact, and maybe it'll make it a little more concrete. So we'll talk through the deposit, L2 transactions, and we'll also go through withdrawals in a little more detail. So the deposit, you send a transaction to a contract. And the key thing is that the contract does some computation, make sure you pay your fees, make sure you lock up your ETH, and then it emits the event. And that event is what we're looking for on the L2 node. That's the authorization that, yes, you locked up your ETH. Yes, all of this is valid. Then the rollup node reads the event, creates a special transaction type on L2, and then we insert these transactions at the start of the block, and then eventually that deposit gets executed on L2. There's a couple more details in there around like gas accounting, but not quite relevant for this talk. So then if you're submitting direct to L2 transaction, you send out your transaction, it gets to the sequencer, and then the sequencer has a set of transactions in kind of its local mempool, and then it creates a block based on that. Then once the sequencer has created its block, the batcher sees, hey, there's a new block. We need to go submit it to L1. So then it takes it, combines it with a bunch of other blocks, does some data transformation, compresses it all, does a little more like data slicing, and then puts it on L1. And then the rollup nodes read all the call data, look for transactions to a specific address, check the authorization on those transactions, and then reassemble the blocks from that submitted data. And then you have, voila, your transaction on L2. Cool, so withdrawals. So withdrawals are a little more complex because you have to manually kind of do the communication across the layers. So to initiate your withdrawal, you send a transaction to L2 to the withdrawal contract. And so the withdrawal contract does several things. It basically creates a commitment to how much you're withdrawing, then burns how much ETH you said you withdraw, emits event to make it easy to index and track it. And then it also touches some L2 state based on kind of the commitment to the withdrawal. And this touching is really important because we'll use that later to verify that you actually burnt your funds on L2 and can kind of withdraw them from the Optimism portal on L1. So after you do this, then you have to wait around for the proposer to say, okay, I've got this new output route. Just go have the proposer submitted on L1. You have to go through the challenge period to say that no one's making a fake withdrawal. And then finally, you can execute your withdrawal on L1. And so what you're doing there is verifying the withdrawal contract or the Optimism portal on L1 when you're doing the withdrawal is verifying that you have a valid proof of your kind of commitment to your withdrawal. So like you have a withdrawal that says, I want 10 ETH back. It says, hey, you actually did have an event or state on L2 that shows that the only way the state could have been true is that if you had actually burnt 10 ETH on L2. So that's like the proof system there. It's basically the overview. There's a couple more details about assembling all of the proofs, but that's kind of mid-level overview, not fully high level. So we have a couple data flows. Let's talk about how it's all assembled. So we've been talking about a bunch of different components, and these are a lot of small modular code bases. So the OP node is about 15,000 lines of code. The OP geth, it's about an extra 1,000 lines of code on top of normal geth. And we find that's kind of what it takes to get another execution engine onto Optimism. The OP batcher and the proposer are around 2,000 lines of code. As we kind of get those more production ready, it'll grow a little bit, but it's likely to remain under 5,000. The contracts around the portal, L2 contracts, all that's around 10,000 lines of code, but that's with all of our tests and supporting code. So none of these are giant, hairy code bases that are all intertangled. They're all kind of off in their own little world. They have clean API boundaries between them, and they're a lot easy to work with, easy to upgrade. And so that's been one of the big pushes with this new architecture. So if you're interested in kind of looking at the code, learning more about it, all of our code is in the Optimism monorepo. We have the OP node code base, the OP Badger code base, the OP Proposer. Those are just top level folders. If you want to look at the Bedrock contracts, it's in packages/contracts Bedrock, self-explanatory. And then we have specifications for how the entire system should work inside the specs folder. Cool. So in summary, Bedrock is a network upgrade to reduce fees and increase implementation simplicity. And we basically talked through all of the architecture that enables this. So this was Introduction to Bedrock's Architecture. Again, I'm Josh Aguto. Find me on Twitter at TriangleSphere. And if you're interested on working with Optimism, or all sorts of positions there, but in particular, we have positions to work on Bedrock. So if this is exciting to you, we're hiring at jobs.optimism.io. Cool. That's it for me. Have a good day, everyone.
Thanks, Joshua. Great presentation. Really appreciate it. Okay, so up next, we have Norswap, who's going to be talking about modular sequencing. Norswap, welcome. Happy to have you. Thanks for being here.
Hey, everyone. Oh, there we go, better. All
Hi.
right. All right. And we are live. Okay, I'm going to be talking to you about modular sequencing. So I want you to know that I did not come up with the title of the talk. Otherwise, it would have been Transaction Ordering is a social construct. Who watches a sequencer? MEV is everywhere. Wow, that's a lot. Let's unpack that. First of all, none of this is future plans. We haven't decided what we're going to do about this stuff. These are just some thoughts and ideas to explore the design space. Okay, so don't make investment decision or whatever based on this. Just don't do anything stupid, really. So modular sequencing. Core talked about how the OP stack is modular. And just like everything else, sequencing is something you can change in the OP stack. Okay, so what's sequencing? Sequencing is picking which transaction to include in blocks and how they are ordered. Okay, and also who sequences these transactions, right? And so who gets to pick and what do they pick? How do they choose? So first we're going to be talking about who. And today it's us, it's OP Labs that runs the sole sequencer. So we get to pick the order of transactions. In practice, we just pick them in the order they arrive. First in, first out. It's very simple. We haven't done a lot of work on this yet. What could go wrong? No comments, but you get some idea. Censorships, all that bad stuff. So what you want to do, really, is decentralize the sequencer, which means having multiple sequencers that cooperate to come up with blocks. Okay. And so what are our goals when we say sequencer decentralization? There are two goals, really. One is liveness, such that if a sequencer were to go down, the network, the L2 chain, keeps progressing anyway. Very important. The other one is censorship resistance. And that's like making sure that we, OP Labs, cannot make your transaction be censored forever, and that nobody can force us to do that either, right? The non-goal of this is safety. Optimism is safe, but the mechanism that we use to ensure safety is not this. It's the fault proofs, okay? So even if there's a single sequencer, then the chain is safe, nobody can steal your money. But decentralization is important nonetheless for questions of censorship resistance and liveness. So how do we decentralize? Like everything, there's a short-term view and a long-term view. There are things that are easy to do and things that are harder, but maybe more interesting. And so at first, the idea that we're playing with is to have a low number of permission sequencers and to have them run round robin. So what that means is that there will be one sequencer. It would take care of a certain number of L2 blocks, like 10 or 100. We need to figure that out and see what's feasible. And then it would be the turn of another sequencer who would do the same, okay? And so if one sequencer is misbehaving or censoring or things like that, he would only be able to do that for a certain number of blocks before another sequencer takes over. And if we diversify the set of sequencer well enough, we put them in different countries, and we make sure that they have some vested interest not to misbehave. So they should be like known entities, they have some reputation, or maybe they put a bond that the governance could take from them if they misbehave. Then we ensure that at least one of these sequencers is going to behave correctly, and the chain will make progress, and your transaction will be included. So there's another model for this, which is interesting. It's called MEVA, and MEVA stands for MEV auctions. We'll talk about MEV a whole lot in the rest of this talk. But MEV, if you don't know what it is, you can think of it as the arbitrage profit, right? If some token is cheap on Uniswap and it's expensive on Velodrome, well, you buy it on Uniswap, sell on Velodrome, you make money. Who gets to make that money? Well, the first person that notices this and does it. And who gets to decide who's first? Well, the sequencer, okay? So the sequencer is able to capture this profit if he's aware of them. And so, yeah, and so since there's a lot of money in this, basically one way that you could say that the sequencer could be decided among a set of sequencers is the sequencer that bids the most gets to sequence the blocks, okay? There are questions here, right? Like you don't want to make it so that the same sequencer wins every single auction. So you still need some kind of mechanism to ensure that this does not degenerate in a really bad scenario. But otherwise, that's a pretty solid one to decentralize and also make sure that we capture some value through MEV. And I'm gonna come back to MEV later. All right. So another model that's interesting is that we could just go and say, well, Optimism will behave like a small blockchain, like a blockchain that's not very decentralized, like some of the blockchains in the Cosmos ecosystem or even Solana. And then we'll run some consensus on all these sequencers, and they will come up with a block. And then that's the block that we'll propose to the L1 chain. Yes, let me see if I need to add something on that. I think I've covered everything. Yeah, and the thing that this small blockchain is not very decentralized doesn't matter, because like I said before, the safety comes from the fault proof. Okay, so even if you have a 51% attack, it doesn't matter. It's just a way to ensure that, again, the network is live, so even if nodes go down, it still works, and nobody can censor, because this mechanism is going to pick different people to propose the block each time. And there are many existing consensus algorithms we could use for this. We could even reuse the proof of stake algorithm from Ethereum, or we could just do something simpler like Tendermint. The reason we don't need to reuse the algorithm from Ethereum is that the Ethereum proof of stake algorithm is made for a huge number of validators, right? And we're only dealing with a small number, at least at first. So I've been saying, yeah, sequencer can misbehave. They can do things they shouldn't do. And so I want to like list the ways in which the sequencer could misbehave. So a sequencer can lie and just include transactions that don't work. If they do that, if they submit bad transaction, they will just be ignored, basically. Other sequencer will just read them and say, this is bullshit, it doesn't work. And so they'll be ignored. The other role of a sequencer, so one role of sequencer is to pick the transaction and propose them. The other role is to submit output roots. Okay, output roots is a commitment to the result of executing the transactions. And if a sequencer submits bad output roots, then the fault proof can prove that these are bad, and the sequencer will be slashed, and so it will lose the bond that deposited. So it's economically unsound to do this. The other things that can go wrong, the sequencer can go down, meaning that he will not do his work, what it's supposed to do. It can censor, and then it can misbehave in terms of MEV, and we will see later what that means. But say we decide that in Optimism we don't want sandwiching, okay? If you don't know what it is, I will explain it later, but or think front running. If we decide that we don't want that, but the sequencer does it anyway, because technically he's able to, then what we can do in those cases where a sequencer is down all the time, he sandwiches when we said that we don't want that, or he censors, then governance can take some action and just ban the sequencer, basically. And that works if the set of sequencer is permissioned, right? If you had to apply to become a sequencer and you had to be accepted, then we can ban you and then you cannot reapply. If it's permissionless, we can't really ban you, right? You'll just go to another server, get a new IP, and then join again. In that case, it's necessary to have a bond that governance can slash and basically take your money. Okay, like you saw, there's a lot of ideas on how we can do this. But the point I want to make is that all these models are compatible with our current architecture. We can just slot them in. And so that's very exciting. We have like a free reign to come up with the best solutions in the short term and then in the long term. All right, second topic on modular sequencing. What can we do sequencing? Well, how do we pick the transactions? And surprise, this is a talk about MEV, okay? You might have heard about MEV, you probably have, but just in case, what is MEV? MEV is value that can, in theory, be extracted by the actor that has the power of ordering transaction. So in Ethereum proof of work, there was the miners. In proof of stake, it's the validator. And on layer 2 on Optimism, it's the sequencer. Some people also call that maximal extractable values, but whatever. So how is MEV extracted? And this is a copy. Okay, there we go. So how do you extract MEV? So there's different kinds of MEVs, and we're gonna review the different major kinds in a bit. That will make it like much clearer. But let's take the example that was before of an arbitrage. If nobody knows that the arbitrage exists, you can just send a transaction, do the arbitrage, boom, you won. Except people might be watching the mempool if it's public. They can see your trade, they can see, this is a profitable trade. What if I do it before this guy? Or I put higher gas fees, so I will be included first. And so people can actually steal your transaction. This is called front running. So in general, you will need to outbid other people. So in ancient times of the Ethereum blockchains, people did exactly this. They did something called price gas auction, which means they put a really high gas price to be the first in the block. And the miners will include them based on the gas price. Then came along a little company called Flashbots, and they released a software called MEV Get. And they offered MEV Get to all the big mining pools. And basically how it works is if you are someone that wants to extract MEV, an arbitrager, and now we call them searchers, MEV searchers, you will send your transaction to Flashbots. Flashbots will relay them to the miners, and miners will include them in their blocks based on how much you pay the miners. A very important thing that Flashbots does compared to price gas auction is that it guarantees that if your transaction is included, it will not revert, which means that basically you can send a lot of money. You'll basically check if you get the arbitrage, and if you get the arbitrage, you send a bunch of money to the sequencer or the miner, etc. Another thing that Flashbots enables is that it enables you to send not only transactions, but also transaction bundles. And so you can see a transaction in the mempool, and you can put trades around, so before and after that. And that enables you to do something called sandwiching. And we'll see that in a second. And people don't like that, usually. This system has a flaw that is not often discussed, is that all the mining pools that run MEV Get, they can see all the trades sent by the searchers, okay? And so if they wanted to, they could front run all the searchers. They could just steal their trades. They don't do this because they know that if they do this, they have a loss of reputation. And then if they're found out, they might be kicked out of Flashbots, which will end up costing them much more money than they can hope to make by basically stealing a transaction. But they could, and this will be important later. Then we switch to proof of stake. And in proof of stake, Flashbots have proposed a new system called MEV Boost. MEV Boost is something called a proposer builder separation system, or PBS. And basically, you get a new entity, which is a block builder that builds the block. And then you got the block proposer, and that's like a validator. So if you're picked as a validator in Ethereum proof of stake, you can ask block builders to bid for the right to pick the transactions in the block. And then the block builders will now act like the mining pools in the previous model. So they will probably run MEV-Geth or something like that to get transaction from the searchers. So why did we change this model? The reason is that after proof of stake, no matter what people say, validation on Ethereum is much more decentralized. There are a lot of small staking pools, there are a lot of small stakers, and we want them to be able to make money. If they get to pick a block, they should also get the MEV money. Unfortunately, you cannot trust everybody with the transactions, right? Because anybody that can see the transaction from Flashbots, from MEV-Geth, they could steal these transactions. And this is okay if you're relying on like 6 mining pools, right? It's a very limited set of people. But if you have thousands or even tens of thousands of validators, it becomes almost impossible to say who stole the transactions. And so instead, you will now centralizing the trust into these block builders, and all the validators can contract the block builders. Okay, so now let's what's MEV? Let's see a few flavors. Arbitrage, if there's a decentralized exchange where price is low, you can buy there and you can sell it higher on another exchange. Very simple. Backrunning simply means capturing some financial opportunity right after the transaction that creates it, right? You want to be first basically, and how to be the first is to be right after. And so the biggest example of this is on lending markets. There might be liquidations because the price has dropped, the price of the collateral dropped. And so these lending platforms want you to take over the collateral for a price in stable coins or something like that. And you will sell it, but they will leave you a margin, which will be your profit. And so people will compete to be the person that liquidates these loans. So that's a case of backrunning. Simply for NFTs, if it's a completely open mint, the first people to mint get the NFT, and so that's a race. You want to be first to mint the NFT. Generalized front running. We saw the example when we say that pools can steal trades from other people. So basically, you'll look at the mempool, you'll look at all the trades, right? And you'll try to see, well, if I were to do the same transactions, could I make money? And if the answer is yes, then you just do that. You just do exactly the same transaction. You will just bid more than the other guy, and then you will take the profit. So that's called generalized front running. Generalized because you're trying this strategy over every single transaction in the mempool. Then we got sandwiching. Okay, sandwiching is kind of complex, but it goes like this. A user makes a big trade, say on Uniswap or something like that. So say he wants to buy ETH with USDC. The MEV searcher says this, sees this, sorry. And so what he's gonna do is gonna do the same trade, but before him. So he's gonna buy ETH for USDC, which pushes the price up. Then the user is gonna make the trade, he's gonna have a worse price. And so that also pushes the price up, right? So if the initial price was X, after the sandwichers buys, it's X plus A, and after the user buys, it's X plus A plus B. And then the sandwicher turns around and sells what he bought in the first step, okay? And basically, he's able to sell that at a higher price than he bought because the user pushed up the price. And so basically, he's making the price worse for the user, and he's pocketing the difference. And so that just makes life shitty for you if you're making a big trade. And people don't like this a lot. There's also something called just-in-time liquidity. I'm not sure I'm going to have time to talk about that. It's a little bit complex to get into all the nuances. But that slide is there, and I will link the slides later. And maybe with time, we'll come back to it. I think I'll leave it if there's some questions about it, basically. So MEV is big business. So this is a screenshot from the Flashbots Explorer, which I took in August, I think. So this is not entirely new, but it gives you, an order of magnitude on these things, right? Like on a month, 8.5 million, in 24 hours, about 6K. And in total, and I'm not sure how long this tracking has been going on, but like 600 million. So this is a massive money that's being made here. it's also highly asymmetric, right? Like some blocks will have like massive MEV and some blocks will have very little MEV, right? Like if you multiply 24 hours, the 24 hours number by 30, you don't get the 8.5 million. So it's very like asymmetrical. About 33% of this MEV is paid to miners. So this is not a lot, right? You would expect people to know the opportunities and basically bid a lot to the miners, like up to 90%. In practice, we don't see this yet. Maybe we'll see that in due time. There've been 18 transactions extracting more than 1 million in MEV. It's interesting. And the biggest one has actually occurred on L2. There were some 5 million plus arbitrage on Arbitrum a while ago. So, you know, MEV on L2 already exists, even though there's no flash bots, even though there's no auction. There are arbitrages to be made, and people will make them. People will make the money. So MEV good, is MEV bad? People often say MEV is bad. That's a naive take. Someone will profit from arbitrage. Like I said, if there's a discrepancy in price, someone will pocket that profit. And I think personally, it might as well be the network that enables those things, and it might go to public goods and to a whole lot of things that benefit everybody, basically, instead of just benefiting some guy that runs a algorithmic trading or some kind of MEV software at home. He's not really doing, like, arbitraging is useful, but there's no reason you should be paid a huge amount of money for it, right? So sandwiches are almost purely zero sum. Someone that does a sandwich is not providing any value on the network. It is possible, so there's been a paper published that says, in some cases, it could be better with sandwiching than not. I really doubt that it is relevant in practice, but you could, in theory, you could construct these scenarios. Just, I mentioned this just to be complete. But, you know, my conviction, 100%, the world would be better off without sandwiches. Nobody likes front running. Just, you know, people, if you smell an opportunity, make a good trade, someone steals from you, it's kind of shitty. And just-in-time liquidity, I didn't get into details, but basically, this one is good for users, but it's bad for liquidity provider, and in turn, that makes it bad for user in the long term. So preventing MEV is dumb, right? People say we should just prevent MEV. You can prevent arbitrages, basically. One way that some people try to prevent MEV is to do this thing called fair ordering, which is first in, first out. And this is not fair at all, because it privileges organizations that can build hardware or infrastructure to reduce latency of MEV extraction. And so, you know, what's fair in that, right? Before, you had at least a competition between guys. It could be at home, and you came up with the cleverest solution. And now you have the same thing that's as flawed, but also only rich organizations can do it. This isn't great. And if you do this, you still have a problem that people will try to start spamming to capture opportunities. This is not hypothetical. It's happened on Ethereum pre-flash bot. It's happening on Solana. It's happening now on Binance Smart Chain, and probably on L2 to some extent, though not quite as bad. So, how, knowing all this, like now we've a big picture of MEV, you know, like it's not good, it's not bad. We need a solution for it. How do we make sure that we capture all this money for the protocol, for the public goods, for the ecosystem? And there are a few solutions for that. So yeah, the goals: capture the value for the protocol, as I just said, make the user experience good for users. And so for me, that means no front running and no sandwiching. This is sometimes something people argue with. They're wrong, you know, like fight me. Maybe we'll get some interesting questions around that. But basically, this works pretty well, and it is actually feasible to achieve that. And I'll talk briefly about how we can do that. And then decentralize effectively. So all the MEV solutions that we came up with must be compatible with sequencer decentralization. As we talked before, it's extremely important to decentralize. So how do we do it? Basically, we want to run some auctions, just like flash bots. One thing we could do is just run MEV guess on the sequencers. The thing is that with Bedrock, we'll have 2-second block time. Okay, and so 2 seconds is not a lot of time. And if you have to, people need to send their transactions to MEVGAF, you need to simulate the blocks, you send that to the sequencer. Maybe the latency starts to add up, and 2 seconds is a little bit too tight. What you could do instead is do MEVA, so that's MEV auctions, via something like MEV Boost. MEV Boost basically does MEV auction, actually. And then you would sell basically the rights to sequence more than one block. You could sell the right to sequence 10 blocks or 100 blocks or something like that. So that's for the mechanism. So making auctions, make sure the protocol captures value. And then we could also impose some rules on how MEV can be captured. And so the simple and effective rule is no front running. If you can't front run, you can also can't sandwich. And you can sort of enforce that. On the short term, you can have governance oversight. So basically we say to the sequencers, guys, it's not allowed to front run. And if they violate this rule, then we can slash them or we can ban them, just like we discussed before. This is not great, right? Because we have to monitor what the sequencer are doing and make sure that they don't do this. And then we have to do a governance vote. It's a lot of like drama and people need to vote, etc. Like I'm of the opinion that generally governance should be minimized whenever possible. In this case, it is indeed possible via technical solutions. Okay, and these technical solutions basically work in 2 steps. The first step is to remove the power of the sequencer to order transactions altogether. And there are basically 2 solutions that are being talked about in the space right now. The first is a first-in, first-out oracle. So Chainlink has a solution identical for sequencing services. Again, this has nothing to do with fairness. Boo. And the other one's called threshold encryption. And that's a solution that a company called Shutter Network is working on. And there may be other people working on that. Yes, there is another company whose name I forgot. Entropy? Maybe Entropy, but I'm not sure. But in both cases, basically you have a network node that provides an ordering for the sequencer to respect, right? In the first in, first out oracle, how that works is that all the nodes in that network, in the first sequencing network, they will receive a bunch of transactions and they will give their ordering of transactions. And if a majority of them are honest, then it's impossible to front run, basically. In the threshold encryption case, you will send your transaction encrypted to nodes in the network. And they will make an ordering of the encrypted transactions. Nobody knows what's doing what. The sequencer will sign on the ordering, and then the network, the Shutter network, for instance, will come together, create a key to decrypt all these transactions. Then you get them decrypted after the sequencer has said, yes, for sure, I will use this ordering. So that's how you take the power away from the sequencer. Now you cannot order anything. And so as a user, if you use this solution, you know that you won't be front run or sandwiches or anything like that. The next step is to reintroduce some form of auctions, because we still want to capture MEV and we still want that value to go through protocol and to public goods. And how you do that is that you conduct 2 kinds of auctions, ideally, at top of block auctions for things that should go at the top of the block. So say last block, after the transaction will reveal, you're like, oh, there's a massive arbitrage now. Well, you can bid to be on top of the next block. And then some transaction also create a massive MEV, just like, let's say, Oracle updates. And so this could be in a public pool, and people could bid to backrun them. The reason why, you could say, well, why don't we just put the Oracle updates encrypted, and then we reveal them, and then people will bid to be on top of the next block? That doesn't quite work. The reason why it doesn't quite work is that people will know the Oracle is coming, and they will start spamming to be by luck after it, right? They'll just like spam a whole lot, and then they'll get to be in the same block after the encrypted Oracle update. So you have to do something special for them. You have to allow backrun auctions, basically. And I think this is the end of, okay, indeed, the end of our presentation. So some conclusion there. So the OP stack in Bedrock is the first incarnation of the OP stack. They are flexible, and you can easily change sequencing. And we will indeed work on that in the future. And the goals with changing sequencing would be to decentralize, for liveness, for censorship resistance, and to extract MEV so that we accrue value to the protocol and the ecosystem and the public goods. What are the best solutions? Well, we're still thinking about that. We're still talking to people in the industry. If you are smart and you have some ideas there, feel free to message me. I love to talk about that stuff. And there are short-term and long-term solutions. On short-term, we can use the governance as a crutch to say, hey, guys, behave or else. But in the long run, there are technical solutions that we can implement that make sure that no matter what, you can't misbehave. All right, I've been NorSwap. You can find me basically everywhere. My handle is NorSwap, including on Twitter. And yeah, if people have questions, I think we have a tiny bit of time.
Hey, NorSwap, good to see you, man.
Hey there, how's it going?
Good. Yeah, thanks for your talk. There were a couple questions, so I'll just kind of ask them to you here directly.
Yeah.
So first question here is just about kind of the fraud proofing and how that works. Is it, somebody individually is submitting that there's kind of a fraudulent thing that's happened? And if that's the case, then, how would you go about preventing people from front running the fraud proof basically and getting the reward for doing so?
Oh, that is such a good question. I love it. Yeah, that's a difficult question. I think like the disappointing answer is that you would go through something like Flashbots that has like sort of a trust agreement not to front run, because otherwise it's really difficult. I've thought about this a little bit. Like we're not quite there yet. We still need to build actually like the technology of the fault proof fully, and this economic part comes even after that. But I've toyed a little bit with like trying to compensate people that like contribute, but it's really difficult because then you can just like sort of copy what other people are doing without doing your own work, and you don't want that either. So it's a real problem.
Gotcha. And then another question that came up was, and I know we have 1 minute left, which might not be enough time, but you mentioned as one of the ways to deal with the cat is here to deal with MEV is sort of threshold encryption is one of the kind of the ideas that that's been put out for managing this. Can you maybe chat a little bit more about like the interaction of threshold encryption and MEV and kind of how that might be a way to mitigate it?
Yeah, so threshold encryption basically, well, threshold encryption I should first explain is you have like this private key and you split it between a bunch of people, and in this case, the nodes of a network. But the public key is known to everybody. And so as a user, you encrypt your transaction with the public key. And only when the nodes come together to create the private key can you decrypt the transactions. And so it's a way to basically remove the power of the sequencer to order the transaction, because now you are ordering encrypted transactions. You have no idea what's going on there. And then the sequencer will commit itself to them. And then later you can reveal. And so it's a way to make sure basically you can't front run or steal opportunities or sandwich and things like that. And if you want to extract MEV, then you need to introduce auction, but you can do that in a way that you can't do these bad things, basically.
Gotcha. Awesome. Okay, cool. Well, thank you so much for being here and running through your talk with us. Modular sequencing, which was actually just a secret MEV talk in disguise, as almost all of them are. But yeah, thanks for being here, NorSwap. Really appreciate you taking the time. And if anybody else has any questions, feel free, as NorSwap mentioned, to grab them out on any platform at NorSwap. Cheers.
Thanks a lot. Love that. See you around.
You too. Awesome. Up next, we're going to have Proto come on and chat about pluggable data availability. We're really excited to have the king of the pineapples here. So Proto, when you're ready, feel free to turn on your video, unmute yourself, and share your screen. Hey, Proto, are you there? Oh, looks like Proto just dropped off. So we're just going to go to a quick break while we get them back in here. And yeah, we'll be right back. Thanks, everybody. Awesome. I think we're back. I think Proto's Zoom crashed. Proto, are you there now? Free to unmute. Oh, there we go. But we can't hear you, unfortunately. Maybe it's the wrong audio source. Still can't hear. I'll let you know if I can. There we go.
Test.
Yeah, you're coming in clear. Awesome. Feel free to
Right.
share your screen when you're ready as well.
Yes, I hope the Zoom does not crash again.
You're coming in
Well
clear.
done.
There you go. Looks great.
Hello. All right, let's get started. Sorry for the delay. So, my presentation is about pluggable data availability. With Optimism, we're both stewarding layer 1 development of increases in data availability, as well as building the technology that uses data availability called rollups. And so I'm going to expand on 4 also called prototank sharding. That's me. And with OP Labs, we're building this rollup technology and building towards the Bedrock release, which uses this data availability. So what does this talk about? Data availability, layer 2 usage, 4, and then some layer 3 design at the end. You can plug and play and build something new. So what is data availability really? Data availability is this primary scaling bottleneck of Ethereum. Over time, the sharding roadmap of Ethereum has changed a lot. Early on, sharding looked like this thing where we had many, many different shards, and they would all have data as well as execution. Over time, we realized that having so many shards would create communication problems if you also try to solve the execution problem. And so instead of trying to solve everything at once, we have this realization where on layer 1, we can just focus on data, securing data, and enabling layer 2s to create this like competitive environment where the execution layer essentially is out of protocol, but secured by layer 1. And so how does this work? The inputs to the functions are secured by layer 1, the outputs are layer 2 concern. And so what we get from securing the inputs is this permissionless ability to reconstruct state. And this allows any honest actor on the layer 2 to compute all the latest states and then contest what the layer 2 output is on layer 1, and then secure the layer 2. So a rollup is really just this combination of data availability and this execution check, the thing that secures the withdrawals going back from layer 2 to layer 1. We have various different types of execution checks. They're also called validity proofs or fault proofs, or previously fraud proofs. So if the sequencer makes a mistake, or if there's a malicious sequencer, they might post the wrong output. They might post a state that's not actually valid. And then you have to prove them wrong on layer 1 to secure the layer 2 outputs and secure withdrawals. Secret rollups have a validity proof, where you prove with secret technology that the rollup performed a certain state transition given layer 1 inputs. Optimistic rollups, they defer the proof, and basically only when there's contention, in the pessimistic case, then you play this interactive game on layer 1 to prove or disprove the output. And so with layer 2, we only really need this data availability for other honest actors on the network to reconstruct the state. Reconstructing the state is very easy if the state was only ever changing like once per month and very, very slowly, and everybody agreed on the state. But the challenge is that layer 2 is quickly changing. New transactions are being confirmed every second. And so all this data that's changing needs to be made available in a permissionless way where we do not rely on the sequencer. And this is what layer 1 offers. This is data availability, hosting data that's changing and that is cannot be relied on from just one actor, from the sequencer, but should be available to everybody. And so if you think about modular blockchains, there's this narrative coming along. You're taking apart the stack, and you see this on layer 1 with the separation of consensus and execution and other blockchains. This enables us to encapsulate complexity and to enable scaling. So abstractly, this looks like we have a data provider and this layer 2 for derivation execution. This is the simplified version. A little bit more complicated is the reality. So we have deposits going, or like layer 1 messages that change layer 2 state from layer 1 to layer 2. And then there is this reverse. We have proposal transactions, which you can think of as an oracle to state what the layer 2 state is and to enable withdrawals. And so we have both data communication as well as this communication for liveness and for this messaging across layers. And then the layer 2 is designed the same way as layer 1, with a consensus layer and an execution layer. And so if you think about the layer 2 state transition function, it's really just a process of incorporating more layer 1 data to extend to layer 2. And then we can prove those layer 2 outputs on layer 1. And so often I see confusion about the proof of stake finalization and the rollup finalization. Before we had proof of stake, we used to use Finalized for layer 2 data that is proven on layer 1. But now that we have proof of stake, we also have this notion of finalized data on layer 1. So if you think about a rollup as a function that consumes inputs, well, then the function is not going to revert if the inputs are not going to revert. And so when the inputs are confirmed on layer 1, then the layer 2 can also be finalized. But it will take some more time for the layer 2 to also be secured on layer 1 for withdrawals. This is this light client type of thing, that the oracle I was talking about, to enable withdrawals. They're separate things. And we're focusing here on just finalization of data, because we're talking about data availability, securing that was what is confirmed. I'll give you a little bit more technical view. So we've been running testnets of the next Bedrock upgrade. Here's an example of a testnet with 2 replicas and 1 sequencer. And then what we're tracking here over time, over the span of 3 hours, is the traversal of the layer 1 chain. These are these colored hashes. And every colored hash is a different layer 1 block. And then a little bit down the graph, you also see the layer 2 chain being traversed and the layer 1 references of the layer 2 chain being traversed. And so over time, we consume new data. And I'll talk more about this data availability. As we're consuming more data, we basically need more capacity to host more users. And so how do we get more capacity? We need to scale the layer 1 data availability. The sharding roadmap has been split up into incremental phases. This has been done before. And now for the latest sharding roadmap, we have this idea of dank sharding based on Dankcloud from the Ethereum Foundation. Basically championing this idea of data availability sampling, where you can distribute data more nicely between many different network nodes. For the short term, we do want data increase, but we are not there yet with the network layer on layer 1 to host 1,000 times increase in data like that, or we're not ready for data availability sampling yet, but we are ready for a smaller increase. And so this is what 4844 is about, is to make this future compatible increase in data availability, going from the approximate 50 to 100 kilobytes data consumed per block now, today, to somewhere closer to 1 megabyte to 2 megabytes per block of data for rollups to consume. And so this is what it will look like with 4844, with the consensus layer, execution layer, and then we have this new data layer essentially attached to the layer 1, where we're hosting these blobs, and these blobs, they function as inputs to host the layer 2 EVM activity. Lifecycle of a blob, or this piece of data that layer 2 transactions are confirmed is like this, where we have the user creating a transaction, the rollup operator bundling the transaction, the layer 1 transaction pool basically propagating the transaction until it can get confirmed, and then the layer 1 confirming the bundle of layer 2 transactions as this blob of layer 2 content. We think of this as a sidecar. It's something outside of the regular beacon block. It's synced separately, but it's this condition where we ensure that the data is available along with the beacon block itself. And then the execution payload of the beacon chain stays in layer 1. The blobs, they are pruned after they have been available for a sufficient amount of time for layer 2 to secure their network. And then it's up to the layer 2 to persist the historical state, which like basically only changes once per month, for other layer 2 users to sync from. And so how do we adopt this kind of new, more scalable type of data? We have this derivation pipeline, which transforms the layer 1 inputs into layer 2 outputs, into the layer 2 blocks as they are processed by the execution engine. There are different stages that we designed as part of the Bedrock upgrade to modularize this transformation. And so traversal, retrieval, and deposit processing, they're all separate processes. And we can swap out the data retrieval process for one that supports the new EIP. With ETH Berlin, we've been doing exactly this. This hackathon of just like a week ago or so, we built a prototype where we took Optimism data, or the Optimism rollup, and implemented the changes necessary to use the 4844 data. And so Prism, we extended with a retrieval API to fetch the blobs. GAF now combines 484 and layer 2 diffs, so we can use all the new changes in the same code base. And on the OP node, we derive data from the blocks and submit new blocks that are being built by the sequencer. Then we have a full layer 2 deployment that looks like this. We have a layer 1 beacon node, layer 1 execution engine, a layer 2 rollup node, and a layer 2 execution engine. You can see the similarities here, where they both have an engine API and a separation of consensus and execution. And then there are these helper modules that make the data, the inputs, and the outputs available to the higher layer. And we can take this and we can stack it. So you could think of a layer 3 that is basically just the same software as we run for layer 2, except stacked on top of the layer 2 instead of the layer 1. And so this is like a thought experiment where what if we just reuse the same code to build a layer 3 and to make things even more scalable. Now what you see here is that this only really works if the blobs, the things that host data in layer 3 are not bubbled up all the way to layer 1, but rather hosted by this layer 2 with a even more scalable data layer. And so you could adopt EIP 484 on layer 2 to host a layer 3, but it would also mean that you'd have to build this alternative, even more scalable data layer. And then, well, how does this compare to Plasma, or how does this compare to these scaling solutions that host their own data? Well, you could separate it from the layer 2 more, where now you have this separate data module to fetch the layer 3 data from. It's less equivalent to what you would like to see from layer 1 technology, but it also does the same job, and you can still stack the rollup node, the proposer, the execution engine. So all this software is the same, but then host the data elsewhere. And so I've been experimenting with these different types of ways, like to further scale what we now know as a rollup, but then in the future as like this modular system that you can reconfigure to become a layer 3 or Plasma or so on. And this is what applicable data availability is about. Once you have this stack of modules, you can configure it the way you like and then build cheaper, better solutions based on the type of application you want to host. If you want to learn more about Bedrock, the modular stack we're building, and the upgrades really of Optimism, you can find this on bedrock.optimism.io. We also have a live testnet you could use. And then there is EIP 4844, this layer 1 scaling effort, which you can contribute to, which you can read more about on eip484.com, and then contribute to on GitHub or in Discord. Any questions?
Thank you, Proto. Just check in the chat to see if there's anything that's come through. It doesn't look like it's so far. Might be worth just, as we're going to jump into a panel about 4844 following this directly. I don't know, maybe if it makes sense to maybe chat a little bit more just as sort of a preamble to that panel about 4844, what it's going to maybe enable, and also just sort of like any other thing you think that's relevant to know ahead of that panel with Tim and the rest of the team.
Right. With 4844, what we're introducing is this different type of data. I think the context that many people may be lacking is how rollups today are hosted and how this compares to rollups in the future will be hosted. Today, we're using call data, which is this type of data that passes through the EVM and was never designed to be used in this way. It was designed to be used as an input for a smart contract, and then it happened to be hijacked in some way for rollups to host and make their data available. In the end, this just means that this type of data does a lot more and is a lot harder to maintain than the type of data that we really need. And so what we're trying to design is the type of data that can be hosted and available without being unsustainable, without growing unbounded. The current EVM on layer 1 and all the inputs is this unbounded type of growth, where the state, the history, and so on is not sustainable to maintain long term. Only when you can prune or reduce the state, then this thing is sustainable to host on regular hardware. And so with layer 2, we're trying to find this balance where we're securing the layer 2, but we're not creating this unsustainable resource usage on layer 1. And so by redesigning this type of data availability, we can make layer 1 a lot more sustainable. We can secure layer 2 at lower costs. And so we can increase capacity for users as well.
Gotcha. Awesome. Yeah, I mean, that's good. That's good context, especially to know that, like, right now, I think the most important takeaway there is that, you know, the chain isn't really set up to do a good job of hosting that data right now, and it's being, you know, almost kind of hacked in. And really kind of the principle behind this change is that, you know, actually doing it the right way versus the kind of like other way. Maybe a quick question while I have you from the chat that came through. A bit of a roll-up 101 question from Abhishek. Just a question around data availability. He says, I understand that roll-ups make a state root commitment to the mainnet. Then where's the actual data of the smart contract stored? If it's a roll-up chain, is it completely down? Well, if it's on roll-up, basically, is it completely on the roll-up chain? And if so, how do I access that data?
All right, so I think I should introduce this notion of blockchain state versus blockchain data history. But you could think of as a blockchain as just a sequence of transactions that has to be available or accessible to people to reproduce a certain state. And so layer 2 makes this sequence of transactions available by bundling them, compressing them, and submitting them to this layer 1, which can host them with higher security guarantees. And then it's up to the users to read all of layer 1 and then reconstruct the state. And then as you reconstruct the state, you can find your layer 2 balances, your layer 2 interactions, everything you might need on layer 2. And then when you want to withdraw from layer 2, all you really have to do from here is to make the layer 2 output, the state root, visible on layer 1. And layer 1, unlike a regular node, does not have its own view of these things happening outside of the EVM. And so rather than what happens in a full node where you can run this layer 2 function to compute the layer 2 state, you need to prove the state with a light client. This light client is essentially a smart contract on layer 1 that can tell you the correct state of layer 2 to be used by other layer 1 contracts that can then process things like withdrawals. The layer 2 state can be proven in several different ways. This is the differences I talked about at the start of my presentation with ZK rollups, optimistic rollups. And in the case of optimistic rollups, what we do is we always post the layer 2 output, but only when somebody disagrees with the output, then we build this game where a challenger and the original poster of the output can battle it out on who is posting the right output and who's posting the wrong claim or output. And so you can secure the claims of layer 2 output to always be correct and to just secure the oracle and then secure the withdrawals.
Gotcha. Okay, awesome. Well, thank you so much, Proto. I think we're going to go to a brief break while we set up the panel for the state of 4844. But yeah, thank you for your time, Proto. And it's always great to have you on ethglobal.tv. And we will transition over to a quick break. So everybody will be back at 2 p.m., which is only about a couple minutes from now. So see you all there soon.
All right. Hey, everyone. Welcome back. So up next, we have a panel on the state of 4884. And we have a really awesome team of experts here to talk to you guys about it. So we've got the legendary Tim Baeko, Terrence Tao, Mofi, and Robert Bayardo. Welcome, guys. Thanks so much for being here.
Thanks for having us.
Yeah, likewise.
Yeah. Cool. I guess, yeah, to kick this off, maybe we could just take a couple minutes doing quick intros, especially because 4844 has been interesting in that it's mostly been spearheaded not by client teams so far. Obviously, you have Terrence here, who's on the client team, but yeah, do y'all want to take just a minute or two and kind of share who you are and how you got working on 4844?
Absolutely. I'm happy to go first. So my name is Roberto Bayardo, and I work at Coinbase. Been there for about a year now. And I'm not on a client team, therefore I was not as overwhelmed by the merge, I think, as everyone else. And we have deep interest in scaling Ethereum, and I was given the opportunity to participate in this for a bit. And so jumped at the opportunity, and hope to keep getting more involved as things go on.
Mofi, you want to go?
Yeah, I go next. Hey, I'm Mofi Taiwo. I work for OP Labs, which is building the Optimism rollup. And I started working on EIP 444 sort of like out of necessity way back like early summer, because it was critical for Optimism to have something like this to keep rollup costs pretty low. And yeah, pretty excited of the opportunity to get this out the door and get it done.
Cool. Terrence.
Hello. Yeah, so hi, I'm Terrence from Prismatic Labs. I am mainly a core dev from the consensus layer. So I've been working around this space since 2018. I started working on proof of stake. Now it's known as the Beacon chain. And last year I've been working on the merge, and also a little bit of MVV stuff here and there. And I've been interested in 4844 actually since ETH Denver this year, February. And I hacked a little something with Proto Lambda, so that was fun. But yeah, I've been mostly watching from the side for the last few months because of like the merge was slightly more important. But yeah, I'm actually really excited to start picking this up again. And hopefully we can get this into Shanghai.
Nice.
Yeah, I think it's worth adding that I think when we say we're interested in the IP 4844, I mean, we're interested in ETH scaling, right? And this is kind of the natural first step to getting where we want to go.
Yeah, absolutely. And yeah, Terrence, you mentioned, this first got prototyped around ETH Denver. And maybe do you want to actually take a minute or two and walk through like how this relates to dank sharding for people who have like no context? Because we have this plan to scale Ethereum massively, like Roberto was saying, and 4844 is kind of one of the first steps towards there. So do you maybe want to just take a minute or two and tell us like what 4844 is and how it relates to like full scaling on Ethereum?
Sure, yeah, happy to. So how do we scale, right? So right now, what we're doing with Bitcoin and Ethereum is just every node download every single data and to verify every data. And that's obviously not going to scale, right? And with how this rollup central roadmap, essentially with our future roadmap, it sounds more like that we will essentially put the data on chain and then run the execution off chain, basically. But in the event of fraud, the execution needs some sort of data to basically prove that where the fraud exists, right? So the nobles. So usually, how it works is that you will have sharding. Basically, means that not every node has to download every single data, but with sharding, it comes data availability sampling, which may take a few years to resolve. And 4844 is essentially the stepping stone, basically say, hey, we will essentially black box the data availability sampling aspect and just make every node download the data as well. But it's a nice future stepping stone for the future. Yeah.
Right. So it's almost like today, all the nodes download and execute everything. With rollups, you can have the nodes only download the data, but not execute every single transaction that happens on the rollups. Eventually, we'd like to get to a spot where like not the nodes don't even have to download all of the data that's gossiped on the network. They can only kind of subsample part of it and know that it was correct. And 4844 is saying like we're gonna add more data capacity for these rollups, but still get everyone to download everything. Is that roughly right? And like you're saying, this kind of came about earlier this year and got like hacked on at ETH Denver. And after that, Mofi, you were like one of the people to actually like start working on, okay, what does a proper prototype look for this? What do we need to do to get this in Geth and Prism first and get all the kinks ironed out? So can you kind of walk through like, what you've been up to over the past few months, what the implementations were like, and yeah, like where things are at now?
Yeah, certainly. Yeah, it's been a wild ride. Past couple months, getting into like EIP 444 was like something I wasn't even aware of it until around like April, even though like it was worked on in ETH Denver. But my first thinking was, okay, we really need this for Optimism. Like gas costs are out of control, right? And at the rate of user growth that we're going, we really need this soon as well. So I basically roll up my sleeves and start working on an implementation. At first, it was basically looked at already existing work, like what Terrence mentioned. He and Proto already had like a proof of, I guess like a proto proof of concept of EIP 4844. There are some things that are missing. First step was basically to take a look at that existing code and extend it, basically. So what I did first was complete the implementation in the execution client. The one that already existed was Geth. So all I had to do was continue working on Geth and have that done. And the next thing was to have a consensus client that also incorporates EIP 444. Even though it's not quite evident, if you look at the spec, there are a lot of like consensus level changes to EIP 444. And so I basically looked at Prism because it's written in Go, and I'm pretty familiar with Go lately. So that was like my client of choice for this, but it really could have been any client. So I looked at a Prism, basically started implementing what's needed to get EIP 444 working. And yeah, that's pretty much mostly what I've been doing for the past couple months. And then there was a point where once both the Geth and Prism implementations were good enough and implemented most of the spec, it made sense to like start integrating things. And that's what gave birth to the first DevNet. So the DevNet is basically a small like network that's running the EIP 444 hard fork. It implements both the consensus and execution level changes to the spec, and it's kind of like our like playground we're using to like test out, how would the spec behave in certain conditions, and what sort of transactions can we like send to it, and testing like the threshold of like the spec itself.
Sweet. Yeah, that was a great overview. Roberto, Terrence, anything you guys want to add on that?
I just want to give a shout out to like Mofi and Roberto and team. It's like having a DevNet now. It's a pretty amazing like accomplishment, right? Just because like we even had the DevNet before the merge, and we had this DevNet before Withdrawal and everything, and it's just like remarkable. And I always find it like impressive and plausible that people go into other people's code base and then able to make like advancements such that. So all the props and all the props go to them.
Yeah, I was going to give props to Mofi specifically as well. I mean, he's really pushed this along consistently. Been an amazing help in providing guidance to those of us jumping in new, completely cold, and being able to get reasonably productive anyway. I also wanted to shout out to Michael DeHoog, who did some work on this from the Coinbase side before I did. So I'm a relative newcomer here. I did some work predominantly on the consensus layer side. Implemented the new style blob verification for so on, for example, and continuing building from there. Hopefully we're going to get the next version of the DevNet up soon, where we have the latest spec changes, for the most part implemented. At least, still remains a little bit of a moving target, but it's starting to settle down.
Nice. And yeah, it is, I believe, the first time that like Coinbase like gets involved in working on a protocol change, at least that I recall. I'm curious, why does Coinbase want to do this? Like, what is the rationale to put engineers on this instead of like the 1,000 other things I suspect you all have to do?
Yeah, it's a great question. And as you know, Tim, I've been talking with Tim since I've started at Coinbase, trying to figure out how we can contribute. And it's there are a lot of competing efforts for time for a Coinbase employee. But ultimately, I mean, I think we realize that we want to raise all boats. We want to build out the ecosystem, and that's not just purely charitable. We view Coinbase as not just trying to be kind of the most easy to use and secure exchange and custodian for crypto out there, but we view it as a broader onboarding mechanism to crypto as well as all of Web3. So if you think about it that way, and look at the kind of number of users we're dealing with, if we took all the roughly 100 million-ish users of Coinbase and tried to dump them on chain, it wouldn't work out so well right now. And we want to do that, right? We want to start blending Coinbase's centralized experiences with more decentralized experiences. Again, provide this very straightforward, easily usable onboarding mechanism and so on. And so in order to get there, we need to scale the ecosystem, right? And the best scaling roadmap out there, we believe, is the Ethereum scaling roadmap. So that's the natural place to contribute. And and so Mike got involved at first. I've joined in. We got a couple other people we're trying to ramp up. And yeah, just really delighted to be a part of this.
Yeah,
Nice.
I can't emphasize enough how much effort Coinbase is putting into this. We have a very good relationship with Coinbase because we're all both in the same boat here. We really want Ethereum to scale, and we also anticipate the huge influx of users as we come in the next couple of years. So it just makes sense for the collaboration effort that we have going on.
Yeah, and maybe to bring it back to how we actually get this done. Terrence, you're on the client team, obviously, and all the client teams have been deep down in the merge for the past year. But some people have started to look over the edge and think about what comes next. What's your general read of how client teams perceive 4844 now? What do they see in terms of the complexity here, the risks? If people have had time to even look into it. But yeah, what's your general read on that front?
Right. So I can give my perspective from the consensus layer client. So my first impression is I really like it. I think it's elegant and I think it's a good stepping stone. And it's funny because if you look at Ethereum history, right, we don't usually just dive into something. We make incremental progress. I think a good example of that is just we ship proof of stake Bitcoin chain first. We didn't just merge, right? We ship this proof of stake Bitcoin chain. We let it run in the wild for 1 year. And then we hard forward to Ethereum. But we didn't merge there, right? Because we want to try to understand how to hard fork in this type of environment. So we take our time, right? And then another example is just hybrid PBS, right? We didn't fully ensure PBS first. We have this hybrid PBS. We use Mad Boost just because we don't want to commit into something. And I think this is a very similar concept. Basically, we are exploring-ish, right? I think my perception is that I think some of the teams also think that I think it's important to get it done, but we want to get it done as safely as possible. We don't want to trade off between quality and speed. For example, I think majority of my time will be spent on testing. And then in terms of just implementation complexity, right, I do think it's a little complicated just because there is this new cryptography primitive such as KZG. And most of the client teams, unfortunately, don't have expert cryptography. We have to work with someone else. And then unfortunately, when you work with other dependencies, it takes longer. It introduces more complexity. But the good thing is that we are using BOS in the current proof of stake. So we do have some experience working with the teams as well. And I think the consensus and the network changes are fairly easy just because we've done that before many times for the hard fork. And then I think majority of the fun part is just client implementation detail, right? For example, we have this concept of optimistic thinking. What can a client do when the data is not available, right? I think using the merge as an example, right? There's probably in Prism, there's 20,000 lines of diff. but there's only like 2,000 lines of diff that's actually important, right? And then we spend the longest time just looking at those 2,000 lines of diff to make sure, hey, this is good, this is good, this is good, this is good. So I will say definitely lots of time on testing and stuff. And I also know like Marius from Jeff has hacked like an EIP 4844 branch for Lighthouse at ETH Berlin. It's super awesome. And Enrique from Teku has also been asking questions on that front. So definitely seeing a lot more progress right now, but overall, I am very bullish.
And do you think introducing, because we're basically introducing a new layer into Ethereum, right? With this EIP, we have like now we like to call it the consensus layer, execution layer. You can almost think of these blobs like a data layer that we're introducing. How does that like change, the client architecture or the testing infrastructure? Like, is this as big as the merge where, the merge we had no way to test the combination of execution and consensus layer clients, and we had to spend, months and months building all that infrastructure? Is adding a data layer similar, or is it actually a bit simpler because, it's still handled by validators on the beacon chain and we have a bunch of infrastructure there?
So yeah, it's a good question. If you asked me that like a year ago, I probably will be more like pessimistic. But if you ask me now, I think like we are like used to this concept of layering, right? For example, we have consensus layer, we have execution layer, and with like all the MBB stuff, we have this builder layer. So like everything is become more layer-ish, and then so like every software implementation is very complicated, but they are as complicated as basically the API between them, right? So we have this concept of engine API, where consensus layer and execution layer basically expose certain things to each other, and that's all they have to understand. And similar with this like data layer, whatever we're calling, right? We will essentially expose this API, such as like getting blob, and stuff like that. So yeah, I would say the complexity is pretty like encapsulated. So that's nice. And we have also done this for the merge. So we're quite experienced at this already. And then it's just testing, and which we have been testing for the last 8 months, right? There's like great people like Perry and everything. We know how to test this with different client combos.
Yeah, I'd just like to jump in and out. I think this is way simpler than the merge. The proto-dang sharding in particular, it's pretty strongly coupled with a consensus layer at this point. It's not like it's adding a completely new independent layer. So I think it really hits a really great balance of taking a step towards that independent data layer without having to go all the way there. So I actually view this as a relatively low risk change. Again, being somewhat young, new to this project and probably naive, but compared to what I saw going on with the merge, this to me seems like almost a piece of cake.
Nice. And like we keep saying how this is what we'll use to scale Ethereum and how rollups will use it. Mofi, do you want to take maybe like a couple minutes to walk through why is this actually better for rollups? Like, how does a rollup use proto-dang sharding to provide lower fees to their users?
Yeah, certainly. So right now, rollups basically have to, after like sending transactions and doing everything in L2, we need to post that data back to L1. It makes it easy for a new node that's joining the network to derive the chain, right? Once that data is available. But posting that data is actually expensive right now today, Ethereum. The main way we do it, well, the only way I think most rollups that I know does it is by using call data. When we create a transaction on L1, all the transactions and state routes and commitments that we roll that up, hence rollup, into a transaction on L1, and that's posted via the call data. But the call data is quite expensive. Over the past couple of months, a couple of rollups, including Optimism, have implemented a couple techniques to reduce the size of that call data, like compression. But overall, it's still not sufficient, especially with the rate of growth we're seeing at L2s. It will eventually be more and more expensive. So what blobs transactions do, which is what EIP 4844 brings, is provide like an alternative source of that rollup data that we need. And also provide like an alternative, but also cheap way to post that data. And the way we're doing it with EIP 4844 is rather than just post it back to L1 as call data, we would use like a special transaction type, call it the blob transaction. And this is kind of goes back to like the data layer that Tim mentioned. So the data that we're posting back to L1 kind of like gets posted to the data layer, not L1 in particular directly. And the economics of this makes it much more cheaper for rollups to do because blob space, data space is cheaper than just using the L1 block space. So that's kind of like that's like one part of like how L2s would be using rollups. The second part is also like in false proofs, right? As a rollup, well, for optimistic rollups in particular, we need to be able to easily dispute any invalid like state root that's been posted on L1. And with EIP 444, this also makes it easier. All we need to do is just change where we're getting the data used for that fraud dispute to use blobs instead. What I like about this design is like it's very easy for optimistic rollups to just plug in what that data source they're using for this. It's either from the data layer or from L1 call data. It doesn't matter. So yeah, that's kind of how it works in a nutshell.
Nice.
And I guess. Oh, sorry. Go ahead.
Oh no, please, Roberto.
I was just going to add, and right. So then, when you can start extending the data layer to implementing the sophisticated, erasure encoding, rather than keeping it with every single consensus layer. But I think one of the things to add, if for the viewers that aren't intimately familiar with the spec, is the blob data doesn't need to be kept around indefinitely by the consensus layer. It can be thrown out. And I think the discussions I've heard so far is probably after a month or so, right? Because I think the main need for that data is for these fraud proofs or availability proofs. And so after the dispute period has elapsed, there's no reason for a standard node to keep that data, which is one of the reasons it can be priced cheaper, for example.
Exactly.
Nice. And so we have all this. L2s are going to use it. It's going to be great. It's going to lower their fees. What's left to do to ship this? Like, first of all, this hasn't been accepted by client teams as part of the next network upgrade yet, because we frankly haven't had time to discuss it in much detail because of the merge. But from like a purely technical perspective, right, to bring this to a spot where like it would be safe to deploy on mainnet, what are like the big things that are missing, and that you're all kind of looking into?
I can go first, then maybe like people can fill in. From my perspective, I do want to start merging the changes into Prism, which means like currently the code is more for like DevNet, but it's not so much for like a production readiness quality. So it will be hard to merge it. So I would definitely want to clean up whatever we have today, merge it with upstream. And at the same time, I do want to like sync with the DevNet a little bit, play with the DevNet, try to break it just to make sure it's robust, it is resilient. And I do think it's very important to write more, right? Because right now I type EIP 4844 on Google and nothing really show up. So I do think we need more like nice resource material such so that to bring more attention to the community. And I think that's like a great way to like push forward.
Yeah. I think the other thing is just more client implementations, right? So we've got Gath, we've got Prism, and they are preliminary, and Terrence is absolutely right. There's a lot more that needs to be done to productionize that code, to test that code, to prove to everyone out there that if we launch this on the mainnet, things won't explode, right? So the other thing I think we really need to do is we need to set up an official test net that I think has EIP 4844 active, where the developers of L2s can actually start creating their next version that takes advantage of it and seeing what benefits it provides.
Yeah, and to add to that, it would also be I think we also need like a proof of concept use case of EIP 444 for like a rollup. Because okay, maybe I'm a little bit salty about access lists, but we don't want to end up in a case where we deploy EIP and people start using it and realize that, oh, the gains are not that much that we expected. We want to like show that this thing actually works. It's a valid use case. We would like use it once it's available, and it'll be a huge boon for the rollup teams. So I think demonstrating this by in particular, like Bedrock, we're actually working with Coinbase to integrate Bedrock with the Bedrock is like the Optimism upgrade that's currently in development, and we want to like integrate it with EIP 444, and then tell like the client teams that, hey, this thing actually works. It's you can see how it works. It's not just vaporware or something. That'll be really, I think, a good way to like convince client teams to like accept it.
Absolutely, yeah. I mean, the back of the envelope math looks great. We expect it to scale, help scaling dramatically. But proof is in the pudding. Once we have code, and a usable system, I think it'll be a lot more convincing.
Right. Yeah. And I'll plus one, Mofi, to your point, where it's like we've had features in the past that we've deployed on Ethereum where like the usage didn't end up being what we expected. So access lists were once. There was once another precompile for interop with Zcash that I think Zcash changed the curve a few months after, so didn't end up working great. So seeing something like a cutting edge rollup implementation that's working on a prototype of 4844, that'd be really valuable. And one thing that 4844 also introduces that's kind of new to Ethereum is basically this idea of KZG commitments, which require a trusted setup. So it's like a new cryptography primitive that we're adding to the network. Mofi, do you want to kind of walk us through what that is at a high level? Like, why do we need to add new cryptography to make this work? And just your general view there.
Yeah. So the data that we're posting to as well, we've already dubbed the data layer that rollups are reusing. We need a way to be able to like prove that a particular piece of that data. We need to be able to prove what that particular piece of the data means, and this is like really useful, for example, in fraud proofs, where rather than sending the entire data set to your fraud proof, you would just send little bits of it, right? And you can like convince the fraud prover that, hey, this data like matches the little piece that you've posted. So what KCG lets us do is it's like a commitment similar to Merkle proofs, but it's different from like Merkle proofs in the sense that it's easier for you to like prove a particular point with the same like proof size, and also it's very easy for you to like extend it. This goes back to what Roberto was saying about like full data availability and erasure codes. So with KCG, it's very like you can like extend like a KCG your data with the KCG, and then easily like make it amenable for data availability. So that's kind of like gets over like the overview of like why we need KCG in that 4844. But it's like new cryptography, like what Tim says, that we're introducing to the consensus spec client. And there's like some unknowns a little bit that we're still trying to figure out. In particular, like what's the most efficient way of like verifying these KCGs. And it's still like an open research question there, but I think as more and more people are like getting into like the spec and taking a look at it, we'll be able to like develop better solutions there.
Yeah, I think it's also worth adding that while it is cutting edge crypto, it's not quite as cutting edge as some of the stuff that's going on in the like ZK EVM world, right? It's a fairly contained, I wouldn't dare say well understood, but it's I don't think it's like we're really inventing brand new stuff here. In some, I'm not a crypto expert, by the way, but I was able to follow a spec fairly easily and go and implement it with the benefit of the proto lambda work and Go KZG libraries and so on. So yeah, I guess I don't want people to be too frightened by that work that's going in there, because I haven't found it terribly intimidating, again, as a non-crypto expert.
Yeah, true. Like the math, like KCG is based on, is pretty old math, like 80s math. It's just recently we're starting to like actually implement it in a production-ish system, and that's where like we're trying to like figure things out.
Yeah, and Mofi in particular has been doing lots of work on optimizations and benchmarking and things like that. So that's another part of the project, and work remains to be done there, making it go faster.
I guess the fun question is like, do you foresee that we just have one crypto library for KZG that all the clients can use, or do you foresee that there will be multiple efforts, like every client team will build their own KZG library?
I think there will be one or two. In particular with Go, we're thinking of using like one particular library that is like written in C, but there are some like particular things with Go and interop with like C code that might prevent us from eventually using that. But I could definitely see like other client teams that perhaps using Rust would probably use that as well. And yeah, it's pretty much mostly two implementations at the most, I think.
Two feels like it would be a sweet spot. One has been a contentious topic in the past for implementing stuff on Ethereum, because we do have this multi-client architecture, and the whole purpose is that if there's a bug, then not all the clients are affected. But then if you have the central point where everybody's using the same library in the background, for the purposes of those operations, you're back to like a single implementation. So hopefully we get to see two high quality ones emerge over time. Yeah,
it's been interesting. We've been trying to sort of figure out where to set that bar, where the appropriate abstraction layer is, where we start sharing code, right? You want to set that as low as possible, but without requiring people to like implement their own very low level bit twiddling to get the crypto right.
Correct. Yeah. And I guess to kind of go back up a little bit, we've talked a lot about 4844 itself and where we're at there. Terrence, do you want to like walk us through what, if you look at like the whole roadmap towards full sharding, what like percentage of it is done with 4844? Like what are like the boxes that we check off? And then what's the stuff that we would need to do over the coming years to get kind of better scale on Ethereum?
Right, I can list a few points. So what 4844 includes, right? What 4844 includes essentially this new transaction type. It's going to be exactly the same format that we'll be using in full sharding. And then most of the execution layer logic required for full sharding is also going to be there. And most of the execution and consensus layer cross verification checking logic will also be there, right? So those three are essentially getting piggybacked by 4844. And like you guys said, like the layer of separation between like this data layer and the consensus layer is also there as well. The concept of sampling blob. Right now, essentially you have one beacon node that samples everything, but with full sharding, you have this committee of validators and beacon nodes sample portions of it. And that's the power of sharding, right? And I think the gas pricing is going to be highly similar as well. So that's very nice, right? So maybe we can talk about like what full sharding has that 4844 doesn't have, right? Full sharding have this like low degree extension for the blob, basically allow 2D sampling. And then it has the actual implementation of the data value sampling. It has builder and proposal separation, because you don't want proposer to essentially sample 32 megabytes of blob. That's just a lot, right? And hopefully some proof of custody stuff as well to ensure there's no lazy validator that just pretend to vote on everything. So yeah, feel free to add on, guys, if I miss anything.
Yeah, I mean, I think to dumb it down a little bit, because it's pretty complicated stuff for someone who's just coming to this. But basically, 4844, every node is still downloading every blob, still storing every blob, with the exception of that what I mentioned earlier, where they can delete it. The full sharding roadmap, once we start doing this erasure coding, you have these committees that can be consulted to reconstruct the data, and so no longer does every node have to store every single thing. So that's why it's called full sharding rather than proto-dank sharding, I guess.
Right, and I guess if you think of it in terms of costs, right now when you use call data, you're storing data that is stored forever by every node, and so that's really expensive. 4844 gives us data that's stored temporarily by every node, so it's like cheaper. And then full dank sharding gives us data that's stored temporarily by only a subset of nodes, and it can be even cheaper. Does that roughly make sense?
Bingo, yeah.
And also, like a little thing that's like a bit different with the, I guess the security of assumptions of the data layer with proto-dank sharding is like you only need like one node that's available, having the data available to be able to like sync up. Whereas with like call data, right, you need like all your peers to have that data available so you can be able to sync up the tip.
Right. Yeah. So you only need to see the data once.
Yeah, I think like that additional like that relaxed assumption makes things is also somewhat contributes to why like blobs are cheaper in some sense, like indirectly. Yeah.
Right, that makes sense. And I guess one final thing I wanted to touch on is there's been tons of like community enthusiasm for 4844. There's been like random people popping out wanting to help. And I'll give a quick shout out to Kane here from Synthetics, who's funded a lot of those to just come and help out with various things. What if someone's like listening to this and they want to get involved in 4844, what are like the things that are most needed right now, and what are the places that they should go or follow to kind of be informed of the latest developments?
Mofi, you want to take that? You've got the best landing page, I think.
Well, yeah, there's of course EIP4844.com. It contains like links to several other resources that I think should help anyone like get ramped up to speed with the spec. We also have like a DevNet, and building a separate DevNet, but that's also another good way to contribute. Basically just running a node in the DevNet, running a node, participating, creating contracts, sending transactions. There's a faucet available in the DevNet that makes it easy for you to, fund yourself and do things with it. So that's where I think I would start. It makes you like get familiar with the network before taking a deep dive into the spec.
Yeah, I was referring to Mofi's HackMD page, where has instructions for getting up and running with the DevNet. So it's a great resource.
Yeah.
Points to lots of our repos and so on.
Shout out to Gabby and the ETHRD Discord for setting up the faucet.
Oh yeah, absolutely. And a bunch of us hang out in the sharded data channel in the Discord. That's another good place to interact with us.
I guess another one is just to write like learning material guide and stuff. Just a lot of people like don't know what 4844 is, and they're probably not gonna read EIP or consensus layer spec, bunch of Python code, right? They probably want to read something that's more like humanly readable, I guess. So yeah, I guess like more education material and more resources, those will be lovely.
Yes, and if you do those, please tweet at me or Mofi or Terrence, and we'll add them. We'll link them on the 4844 website for sure.
Yeah, and if any testing experts out there, we have a lot of work to do there. For example, I think that's one area where there's it's an easier way to get started, right? You don't have to understand the entire spec. You can pick a little piece of it and take a look at the code we've written and how poorly tested it is so far, and dive in from there.
Yeah, nice. There's a lot of low-hanging fruit there.
Yeah, so testing is a big one. Cool. And so if you have testing experience, please give us a shout on Twitter, emails, on the website, and we'll find something for you to do.
Yeah, and optimization and benchmarking critically important here. I mean, this we've mentioned it a few times already. This new crypto is pretty expensive. If you don't do it right, you introduce denial of service factors. We want to make sure that doesn't happen. So that's why that area of work is also important, and plenty more to do there.
Sweet. I think this is a good place to wrap up. So we've covered what the EIP is, why it's valuable, where we're at, what you can do if you want to get involved. Do any of you have any kind of closing thoughts you wanted to share with folks?
I guess to close, we really need rollups to be cheap. If you want to send your NFTs and mint them really cheaply, this is the way to go.
I think my only closing thoughts is that this is something we really love to target for the Shanghai release. I personally believe it's not too ambitious of a change to slip beyond that, but we'll do our best to make our case through stuff that works. Hopefully we'll get there.
My thoughts is, I think besides withdrawal, scaling is probably the most important thing to work on post-merge, because like Danny said, we're sustainable and we have security. So scalability is next. And it's funny, when I first started working on this space back in 2018, I wanted to work on sharding for the longest time. And then finally, now this is the time to work on sharding. So yeah.
Nice. Well, yeah, I think that's a great place to wrap up. Thanks a lot, guys, for coming on. I appreciate you all taking the time, and thanks to ETH Global for hosting us.
Yeah, thanks for having us.
Thank you.
Yeah,
Thank
you guys so much. Yeah, thanks for all of the information. It was a really awesome panel. Appreciate you guys all being here. Thanks.
Okay, bye.
Bye. Okay, up next we have Mark Dawson from Quix, who is going to talk to us next. Hey, Mark, thanks for joining us.
Hey, Katie, great to be here.
Yeah, thanks for being here for sure. All right, I will hand it over to you. You can go ahead and get started.
Okay, great. I will go ahead and do a screen share. Okay, great. Can you see that, Katie? Is that going okay? Awesome,
yeah,
yes.
We're good to go, thanks.
Okay, cool. Hey, everybody. My name is Mark Dawson, and I'm the co-founder of Quix. And I'm going to talk about the Optimism NFT ecosystem today. So that'll be a little bit of a change of pace from some of the more technical talks. This one will be a little more fun and a little bit less technical. Let me tell you a little bit about Quix. We're the largest NFT marketplace on Optimism. We're a top 5 delegate in the Optimism NFT governance system. So you might have heard about the Token House and the Citizens House. We're a top 5 delegate in the Token House. So we'll be voting on proposals for the governance fund. If you're trading on Quix, the average gas fee is 14 cents compared to OpenSea or like ETH mainnet, which will be today usually about $2 or $3. A few months ago, you might remember it was close to like $50. So we're probably 10x or 20x, 30x cheaper than Ethereum mainnet, and we've traded about 2,500 ETH in volume so far. We launched about I think I lost my my screen. Let me make sure it comes back. Sorry, everyone. We launched Quix in December 2021, right around the time that Optimism removed its whitelist for apps. And we are coming back. And basically, I want to spend time today talking about like if you're a creator, like how you can get involved in the NFT ecosystem, Or Katie, can you see the screen okay?
Yes.
I'll assume yes. Okay, and it's full screen.
Yep, it sure is.
Okay, great. Thanks so much. So if you're an NFT creator, you probably have used L1 Ethereum, maybe Solana, maybe Polygon. The Optimism NFT ecosystem is much smaller today than the other ecosystems, but it's very exciting for a few reasons. So why would you be excited to use layer 2 NFTs? Layer 2s are of course like faster and cheaper. And that sounds great, but it's actually even more exciting because it's like 10x faster, maybe 100x cheaper. So it means that you're going to be doing totally different things. The way I like to say it is that like layer 1 Ethereum is like you're driving a car, and layer 2, like Optimism, means that you're going to be flying in a plane. So you're going to be taking trips that you didn't take before. So what kind of trips might those be? So the breakout use cases that I'll highlight so far: creator-owned smart contracts. Mirror.xyz is one of the biggest Web3 blogging platforms out there. And historically, they had one big smart contract on Ethereum mainnet so that people didn't have to deploy a smart contract for every new blog post that they made. That saves on gas, but the problem is that your writing NFTs can be mixed with like other people's blog posts, which creates kind of a confusing experience on OpenSea or Marketplace. And it can just like make your work harder to find. So earlier this year, Mirror moved over to Optimism. And now when you're creating a blog post on Mirror, you can deploy your blog post as its own contract on Optimism. It's going to cost only maybe like $5 compared to maybe like $50 to $100 on mainnet. And on our marketplace, you can trade the writing NFTs, and they're all their own distinct collections. And like on Etherscan, they're all going to be their own contracts. So that's pretty exciting and pretty creator friendly. Another cool use case of layer 2s is reputation NFTs. So just about a month ago, Rabbit Hole, which is a big like Web3 education platform, launched some badges on our platform. So you can collect these NFTs to prove that maybe you learned a new skill set or that you completed some task. So maybe you learned about some DeFi protocol and now you want a reputation NFT. That doesn't really make that much sense to do on Ethereum mainnet because you're probably not going to make a lot of money off of the like badge NFT. And so you don't want to be paying like $5 to mint it. But on Optimism, you can mint it for like 10 cents. And what's really exciting for me is these reputation NFTs today, they're mostly about collecting, but eventually they could be about unlocking maybe like some special skill set. I think all these, like if we put more things on chain, like if we give you more badges for all the stuff you're doing, that gives developers a richer set of data to build on top of. So my hope is that like if I've done a lot of DeFi activities, maybe when I visit a Web3 site, it'll kind of recommend to me DeFi activities or something like that. So reputation NFTs are a great use case of layer 2s. Composable NFTs are another one. That means NFTs that combine with each other. So Dope Wars is an NFT project that was released actually like mid to late 2021. So they're really early on it. They began on Ethereum and they wanted to have these characters that they could equip items to. So, they have these characters called hustlers and you want to give them some like sneakers. And the sneakers are NFTs and the hustlers are an NFT and you want to combine them. The problem on Ethereum mainnet, once again, is that you're going to be looking at like a $5 gas fee for doing that. And really, as L1 Ethereum gets more expensive, the only things that you're going to want to be doing on L1 Ethereum are things that have direct financial benefit. So maybe you'll trade on L1 Ethereum, but you're probably not going to want to like equip or interact with your NFTs on L1 Ethereum. So they built their own bridge actually, which is pretty cool, and bridged their collection to Optimism. And that's just the beginning. There's a lot more I'll say about composable NFTs later. Another great use case is Dragonia. They're an on-chain gaming platform. I think one of the first on-chain games on Optimism. So with these, you buy these Dragon Trainer NFTs and they can battle each other. And it's like a little bit like Pokemon, but much more simple. What's cool is that the battle interactions happen on chain. Once again, as you're putting more stuff on chain and doing slightly less financial activity on chain, you can't be doing that on Ethereum mainnet because it'll be too expensive. So you're going to want a layer 2 like Optimism. These are all live projects today. And there's a bunch that I didn't get to talk about. So let me go ahead and focus on the ecosystem. We have about 40,000 people trading today on Optimism, 40,000 unique wallets, I should say. And a lot of those are in Thailand and East Asia, which is pretty cool. Many are pre-existing NFT communities. So crypto testers, which is this guy with the OP hat and he's green. The crypto testers is a community that's existed for a couple of years, and their goal is to test out new crypto protocols. They issued their community membership NFTs on Optimism, which we were really excited about. And those are trading on Quix today. The other NFTs I'll point out here, a lot of them are pure art NFTs. So this top one is called Optimism, and that's from our community in Thailand. They have a very active community and some really strong developers over there. A lot of them will like review smart contracts that we put out, and they've created their own launchpad. This middle one that looks like you can't quite tell what it is, that's called Ganland, and that's AI generated art by a project called Fractal Visions, and that's based in Colorado, I believe, in the United States. We have Board Town in the top right. This is like the animal looking ghost. And that is a collection, again, from creators in Thailand. That one's really fun. The Board Town Animal Ghost project has the honor, I think, of being the first collection that was copied by like a scammer and put on OpenSea. So like a scammer, copied all the all the art and launched their collection on Ethereum mainnet. And I always take that as a sign that you're doing something right when people want to copy your work and take it to other places. Because early when you're establishing an ecosystem, of course, the first thing that's going to happen is people are going to sort of copy what happens on layer 1 Ethereum and try it on Optimism. But now people are copying what's happening on Optimism and trying to put it on layer 1. So that's pretty cool. This one of the person in the helmet is called Motorheads. And that is a collection by a designer actually at OP Labs named JVMI. And this collection is kind of about video games and early 2000s nostalgia. So like there is this really cool mint page that had a Game Boy on it. And that one's a pure art project that's quickly developing its own community. And then this one that's kind of cut off a little bit. This is a duck called Usagi Duck. And that's from an artist in Japan. And she made this collection of 2,000 ducks that all look very funny and whimsical. So this is a taste of some of the communities and artwork on Quix today that I wanted to give a shout out to. And another cool thing is that many of these communities launched using our launchpad on Quix. So I'll take a minute to talk about that. Our launchpad is a creator-owned smart contract tool that you can use to deploy your collection, and will also create a mint page for you. And you can have your own allow list, and you can also reserve some for your core team and do the drop like directly on our website. If you're a little more sophisticated, you can, of course, make your own smart contracts and make your own mint page. And we'll also index and pull those collections into the marketplace. So we're just a big secondary marketplace, and we're going to pull all the NFTs deployed on Optimism into our marketplace. So out of these ones, Ganland, Motorheads, Boardtown, and Usagi Duck all used our launchpad, and Optimism created their own website, and I think Crypto Testers did as well. And Optimism also created their own launchpad, I think, which is pretty cool. There's also a bunch of other launchpad tools and creator tools on Optimism, so you can find them at NiftyKit and Mintplex, and there might be another one. But yeah, more and more creator tools coming to Optimism. I'll say it's still a very tightly knit and community, so a lot of these collections will work with each other. So like the Motorheads will often like cross promote with the Boardtown NFTs, for example. So you might be asking what's next for Optimism NFTs, because so far the ecosystem is collections that you might see on mainnet. So like the art ones, the tradable community pieces. We expect that to continue to grow, but we have these really exciting things in the pipeline. So we have an NFT bridge coming up that allows you to take an NFT on layer 1 Ethereum and bridge it over to Optimism. I'm gonna discuss that more at length in a couple minutes. We're excited about these reputation NFTs. So that's something similar to what Rabbit Hole is doing. These, sometimes we call them badges. The difference here is that these are often earned rather than purchased, and they're often not really good assets for trading because they mean that you did something right. So like if you completed a quest on Rabbit Hole, there's no reason for me to purchase that. But it's still really interesting, and I'll talk a bit more about reputation NFTs. And then composable NFTs. So that's what I was talking about with Dope Wars. There's a developer named Austin Griffith. He has a pretty big following on Twitter, so you might have heard of him. And he has proposed this ERC called ERC 4883, which is a specification for composable NFTs that can like fit together. He created a collection on Optimism called Optimistic Loogies, where you can have these little characters and you can equip items to them like bow ties or lipstick. And there's a specification for doing that. So we're excited to help people make composable NFTs. And we think that's really something special that you're going to want to do on a layer 2 rather than on mainnet Ethereum. So let me talk a bit about the NFT bridge. That is slated for launch in October 2022. So that's very soon. We have development was led by a software engineer named Sam Goldman on the Quicks team. And he has contributed that to the Optimism code base. So that will be maintained by OP Labs. When we were designing it, our goals were first and foremost to be credibly neutral. So like no fees or anything like that. And then fast, easy, and permissionless. We want the structure and semantics of the bridge and especially of the corresponding smart contracts to be very close to layer 1. And I think you'll find that that's a theme of a lot of projects on Optimism because of the EVM equivalence. It makes it easy to be very similar to layer 1 smart contracts and projects. And we want all the tooling around NFTs that you have on layer 1 to also work great on layer 2. So that means, for example, that every layer 1 collection that is a smart contract is going to have a mirrored smart contract on Optimism. We're not going to try and make, for example, one giant contract and deploy everything on that one contract. And the reason for that is that a contract for NFTs is often synonymous with a collection. And we want to keep that boundary there. We're using the official Optimism cross-domain messenger. And what that means is that we're using the official Optimism protocol to handle cross-layer communication. This is different than using an Oracle or a service like Layer 0. Layer 0 Labs created these fun omni-chain NFTs earlier this year, starting with the Ghostly Goods collection. And that was really fun, but they did use a Web 2 style Oracle to handle the message passing, which is cool because you can send NFTs, in minutes, but you might have security concerns. So this is a highly secure bridge. The trade-off there is that it might be a little bit slower than using an Oracle. So if you're going from layer 1 to layer 2, it's going to be about 15 minutes. I think after the Bedrock upgrade for Optimism, it's going to be more like 5 minutes. To go from layer 2 to layer 1, it's going to take a week because it has to go through the challenge period for the fault proofs. So for this bridge, it's like highly secure and therefore a little bit slower. In the future, there might be a fast bridge that uses like an Oracle like layer 0, but for this bridge, for the very first bridge in the Optimism NFT ecosystem, and one of the first official bridges in the for one of the first official bridges in the layer 2 NFT world generally, we wanted it to be as secure as possible. And then I'll just briefly discuss how it works a little bit. So it's an escrow system. So it just locks your layer 1 NFT in a layer 1 smart contract, and then sends the message to layer 2, and then mints a corresponding NFT on layer 2. And then that NFT can be passed around. It can be traded around. And then whenever you want to leave Optimism, you can burn that NFT and it will unlock the layer 1 asset and give it back to you. So this is how ERC20 bridges work often. And it's how the Optimism ERC20 bridge works. And this means that the asset is just as valuable on Optimism as it is on layer 1, because owning the NFT on Optimism means that you own the asset on layer 1. So that is a deep dive on the NFT bridge. I wanted to talk about how we plan to use the bridge in our marketplace. So bridging, there's a technical aspect to bridging, which is what I talked about with the message passing and with the smart contracts. But what might be even more interesting is the social aspects to bridging. So NFTs are a little bit different from ERC20 tokens because they often have artwork and a community associated with it. And a community is kind of all you have in a lot of cases. And so it's going to be the NFT owners at the end of the day that have to decide to bridge to Optimism to take advantage of the cheaper fees and new design possibilities with the lower fees and faster transaction times. It's unlikely, for example, that the core developers of a project can just tell everyone to bridge. And so for that reason, we want to make it really easy for owners to bridge to Optimism. And also we want to make it easy for them to list across layers. So this is like the Boardtom project. And this is how a collection is laid out on Quicks today. You're going to see a bunch of the assets like in a grid format. And I just put this here to show you what like a unified collection looks like. And for layer 1 collections, we want them to still be unified, even if they're partly bridged. So someone might point out, for example, that there is a Polygon NFT bridge and that OpenSea currently supports Ethereum and Polygon's much cheaper. So why isn't everyone just bridging their Ethereum NFTs to Polygon and trading them on OpenSea? Since there's like technically support for that. And the answer is that the platform is not designed to encourage bridging, because once you bridge, let's say you have a Bored Ape, if you bridge the Bored Ape to Polygon, that's going to show up as a completely different collection on OpenSea. And people might think it's a scam, it's going to be weird, all the activity is going to be segregated between the two collections. You're probably not going to be able to get as high of a price for that reason, because people might think it's less credible. And so the way we're designing Quicks is we want it to be designed so that you bridge NFTs. So we're soon going to begin indexing and showing layer 1 NFTs in your profile in Quicks. And we're doing that not because we're about to also have trading happen on layer 1, because we're an Optimism NFT marketplace, but it's so that you can have the opportunity to bridge your L1 assets and begin trading them on Optimism. So if you have a Bored Ape, for example, on Quicks, what you'll be able to do is, let's say you list your Bored Ape on Quicks, then you'll be able to see the Bored Ape and its attributes and its rarities and its activity in the same place as all of the layer 1 NFTs. So there's still going to be 10,000 items in the collection, if that's how many are on layer 1, and it'll show maybe like 100 of them have been bridged and are for sale. But we'll still do our best to pull in all the activity and all the context from layer 1 that you want to see. And this is really important because when you're trading NFTs, getting context and feeling like you're a part of the bigger community is really important. So that is kind of how at the social layer, we're encouraging people to list their NFTs on Optimism, to bridge to Optimism, and to use them on Optimism. And if we do this correctly, then this is just going to be a pure win for everyone, because the lower fees on Optimism mean that you can have lower price collections. So on Ethereum today, if your floor price for your NFT collection falls below a certain threshold, the gas fees make it not worth trading anymore. And that can be really sad for the collection. So you might be able to breathe life into that collection by bridging it to Optimism, because it allows trading to kind of continue, even if it's only worth a few dollars. And in fact, a lot of the collections on Optimism are only worth a few dollars. And we also allow creators to create a custom contract for the Optimism collection. So what I mean by that is when you bridge an asset from Ethereum to Optimism, we deploy a standard plain vanilla Open Zeppelin NFT contract for you. That's great for trading and transferring and collecting. But let's say that you now want to add the ability to, I don't know, have your, two NFTs have a baby, for example. I don't know. Let's say these two Bored Apes can have a little baby Bored Ape. You're going to need to add some functionality in your smart contract to do that. So if you're looking to extend your layer 1 NFT collection, yeah, CryptoKitties throwback. Thanks, Jacob. If you're looking to extend your NFT collection, you might want to combine that with bridging. So because the way the bridge works, remember, is you escrow the layer 1 asset and then you mint a new asset on Optimism. But you can be minting that in a standard ERC 721 contract, or you can be minting it in a custom one that adds some functionality. So the goal for bridging for us is that you're opening up a new design space, you're doing things that you haven't been doing before, and that we're helping your community scale. And the other piece to that I'll add is that we're looking to integrate our bridge into our launchpad. So we're kind of in a weird purgatory period today with layer 2 adoption, because layer 1 definitely works and layer 2s, they work, but there hasn't been a social consensus about which layer 2s to pick, or their security hasn't been as battle tested as layer 1 Ethereum, obviously. And so let's say you want to launch a companion collection for your L1 collection, or you want to launch a brand new collection and you're excited about Optimism, but you want to give the community the ability to bridge back to layer 1. We're going to add into our launchpad the ability for you to launch a collection on Optimism or on Ethereum with like bridging kind of pre-built in as part of the plan. Now you don't need to have that at launch, but we want to once again give the design affordance to everyone to say hey, think about scaling right now, because when the next bull market kicks off, gas fees might crush your community. So let's pick a place at launch for us all to move to, or maybe even you mint the token originally on Optimism, but if you don't want to be on Optimism in the future, you can bridge back to layer 1 Ethereum. you can kind of plan that out. So we're still in the design phases of like what a cross-layer launchpad looks like, where you get the benefits of launching on Optimism while still having the ability to exit to layer 1 if you want. So that's like a really active area of design and like product research for us. So that concludes the overview I have of the Optimism NFT ecosystem. I have a couple minutes left, so what I might do is just show you our platform. So this is the Quix website, and you can see we're featuring our mirror writing NFTs. We've recently been doing a OP OG NFT drop, so we gave this early optimist. We name him Tim or Timmy for Optimism. And we gave this to like people who were trading on Quix, you know, in the early days. And so it's really easy to get started. We're at qx.app, and we encourage anyone who's interested to join, especially one of the like lower cost NFT communities, and hop in the Discord. And if you're a developer, you know, consider checking out what you can build on layer 2. And that kind of wraps up my presentation. Do I still have some time, Katie, or should I keep going or turn it back over to you all?
Hey, Mark, I'm gonna jump in for Katie. Good to see you here. I think we'll just double check if there's any questions or anything, but you're free to use a couple more minutes if you have some more stuff to chat about. Otherwise, I'm just gonna check if there's any questions. So give me 1 second here.
Cool. Yeah, I mean, I can of course do ecosystem spotlights all day long because we have so many. Cool. I'll just keep spotlighting some groups in the ecosystem. So this is called Draconic Egg, and it was fun because these were originally egg NFTs, and then they hatched at a specific day, which is kind of like a reveal. These were actually generated with I forget which model, but it was like an AI that made all these, which is cool to me anyway. And we've actually seen a lot of dragon themed collections. The other one I'll spotlight is Dragonia, and this is like the play to earn game. So these dragon trainers can like fight each other. And that's a great layer 2 use case because you don't want to be paying O1 gas fees when you're interacting with the game on chain. And let me go to this explore page. We're in the middle of the Optimism Quest. If you haven't heard of that, definitely go check it out. This is a way to explore the ecosystem and earn these fun NFTs. And you can look at your NFTs on Quix. So if you've traded on Uniswap, you get one. If you've used synthetics, you get one. There's, you know, all sorts of Velodrome is another big decentralized exchange type protocol. If you're writing any article on Mirror, that's going to deploy an Optimism and show up on Quix, and it'll trade on Quix. So a lot of fun announcements, like this group called SyncSwap announced their mission statement and did it on Mirror, and you know they traded several $1,000s worth of that blog post on Quix and on Optimism, which is pretty fun. And
Very cool.
How am I doing on time, Jacob?
I mean, we're right on time. I mean, we can wrap up here. Really cool to have you here, Mark. I mean, Quix was, I guess at the time, Quixotic was probably the first like meaningful transaction I did on Optimism. Otherwise, instead of just like sending money to somebody. So it's really cool to have you be a part of this.
Yeah, I'm so excited. And yeah, I guess the Easter egg is we used to be called Quixotic, but we got the feedback that was like really hard to say and hard to spell. So we shortened it to Quix.
I like the name. It's nice. Very cool.
Thanks. Yeah, it's quick. Quick to transaction optimism. So
Love it. Awesome.
Cool.
Well, thank you so much, and I love the work that you're doing, especially around education and tying NFTs to getting people to learn more about and just incentivize exploring what's out there on the Optimism network. So it's been awesome to have you here. Thanks, Mark. Appreciate you being here.
Thanks. Yeah, it's been great to be here.
Awesome. Okay, cool. Well, that about wraps it up on our end. So thank you, Mark, again. And then, yeah, on behalf of Katie and I, thank you so much for being a part of this event and for joining us to hear more about the Optimism ecosystem, both from the people working on it and from some of the people that are deploying on top of it. So yeah, really excited to be finishing this conversation up. And thanks so much. If you're going to want to watch this later, it's available on our YouTube page at ETH Global on YouTube. But otherwise, thank you so much for joining us. And we hope to see you at our next summit tomorrow. Cheers.